I'll go over where you can access this in a minute. And since two of you are new, and maybe the rest of you need a little bit of review on it, but just in case, here's the deal. When you go to Blackboard in this course, okay, y'all are familiar with Blackboard, everybody, right? Okay. The home page of Blackboard for this course, there will be a series of blue tabs over on the left-hand column. And this year, they split them up into groups. In that first group, somewhere about the middle, maybe the third one or so there, it says something like syllabus and book information or something like that. If you click on that, you'll see the syllabus for this course. Okay? It's been updated. Everything should be correct now. Then, just below that, there's one that says instructor information and office hours or something like that. If you click on that, then you'll see my locator card, which shows, well, information at the top, my phone number, my office number, email address, or some sort of stuff like that. And then the whole week ahead of you, by hours, by days, and it shows when I'm on campus, when I'm off campus, when I'm, which campus I'm on, when I'm in class and out of class, when I have office hours, when I have lunch or whatever. That's all on that for every day of the week, Monday through Friday. Okay, then if you go into the second grouping, somewhere about the bottom 2/3 of that, you'll see one that says handouts, PPTs, and more. That's PowerPoints and more. And just when I was walking in, down the hall to get here, I happened to think, have I put the PowerPoints on here yet? I don't think I have I? Okay. Sorry about that. Okay. I realized what happened. You see, for all my other classes, I have a flash drive, and it has all the PowerPoints on that. This class, however, has a CD, DVD type thing. Well, when I was putting together my Blackboard, I was at home when my wife had surgery, and I didn't have the DVD. That's sort of awkward to carry it, get it broken or something. So I had it here, and I just realized I haven't loaded those yet. So I'll try to load those. Okay. But there's other stuff out there right now, okay, under handouts, PowerPoints, and more. Here's the first. The YouTube videos for this course. Now you might say, we've met 3 times. There's a whole string of videos. So if you see that, Physical Science PHS111 YouTube videos, you click on that, you see a whole bunch of videos. Now near the top, it may be at the top or near the top, you'll see one that says syllabus. Okay, that one please read. Okay, now remember, I have the syllabus out there. You can read that if you want to. For sure, do. But this one, I go over the syllabus. Now, it's not exactly the same syllabus because it's the one I used last fall, and so it's talking about September, October, November, or something like that. Yeah, we're not in that term yet, still. But the content is still the same. The basic content is the same. How we run the course is the same. All the stuff is the same. And you can hear me talk about it if you want to hear me talk about it. Okay, then I also talk about the research paper, which is due. And remember, and I haven't said it yet, but also under handouts, PowerPoints, and more, there's a research paper instruction. You can read them there, or you can hear me talk about them on the YouTube video. Okay? Now I'll be talking about August and September, whereas now we're talking about January and February. Okay? So, that's out there, the YouTube. Now, after that first one, go to the bottom of the list, and you might have to scroll up for a while, and then you'll see the first class we did, the one on Tuesday. And these are big classes because they go about 4.5 hours, not quite, but close to it. Okay? So it's quite a big, lengthy video, but it covers everything in Chapter 14. And we finished Chapter 14 last time. Okay? So what that means is today we start in 15, and then we'll have a 2-hour lab. We'll do about 2 hours in 15, and we'll have a 2-hour lab from 14, though it's not exactly from there, but it is related to that. And then the last 30 minutes is the test on Chapter 14. This is a mini-term course. It flies by. We're covering something like 7 chapters in 8 weeks. So we have a chapter a week. So we're almost going to average a chapter a week, a test a week, and a lab a week. Some weeks we may even have 2 labs. So it's going to go by pretty quickly. Okay? So now 2 of you are brand new here. Several of you missed some of the class last time. If not all the class last time. So if you don't feel ready for the test today, you don't have to take it today, but please try to get caught up, look at the video, do it, read the chapter, do everything that the video instructs you to do, and then try to get the test taken, if possible, within a week, okay? You can take longer if you need it, but please, we're going to have another test within a week, so please don't get too far behind, okay? So we will have that test the last 30 minutes, but I don't want you taking it unless you feel ready to take it. Okay? And that's all of you, whether you were here in class or not. Okay, so that's the YouTube videos. Now the reason I keep them all out there is in case, what if my computer dies, the system goes down, something happens and I can't record a class. Well, you have it recorded from the last time I taught it, and it won't match completely, but it'll be close. Okay? So they'll always be there. Something will be there that you can see. Okay? So, and as soon as I finish, like when I did loaded 14 last time, I deleted 14 from last time, from the previous time. Okay? When we do today's, if there's something that's equivalent today, I'll delete that. All right. So that's the first thing under, yes? Okay, I just said, I forgot, when I was loading PowerPoints, I didn't have my CD at home, because it was last week when my wife was having surgery, okay? And it just dawned on me when I was walking down the hall. I just said all this, that I hadn't loaded those. So I'm going to try to remember to take them over to the Birmingham campus tomorrow, and I either load them tonight when I'm at home, or no, I'm not going to load them tonight. My wife has tickets to the UAB basketball game, so I won't have any time to load them tonight. But I'll try to get them loaded tomorrow when I'm on the Birmingham campus. Sometimes it gets crazy over there, but hopefully I'll get them loaded then. If not, then Monday morning, no. Do y'all realize this? It's sort of a good news, bad news situation. The bad news is Monday's a holiday. There's no classes. I'm sorry. Okay? But the good news is we meet on Tuesday and Thursday, so it won't affect us any. Okay? So we'll have a class as usual next week, but there are no Monday classes. I was going to say Monday, I have 2 hours at the beginning of the day and 2 hours at the end of the day. I can load those. I don't on Monday, but if I take them home with me, I have them at home, and I can load them for Monday. Okay. So, in addition to the YouTube videos, then the research paper is in there. And then, I think some student showed me, sent these to me many years ago. They were 10 incredibly beautiful photographs taken by the Hubble Space Telescope. And you'll find those in there. You can click on those and see them. There might be some text that goes with them. I don't remember if that carried through or not. But anyway, the pictures are just incredible. Nothing you need to do with them, but just they're really neat pictures. Then there's another file that a student sent me, I think like a different student, that was Space Objects in Perspective. I talked about this last time for those who were here. It shows a representation of the Earth and Venus and Mars and the Moon giving relative sizes, and Mercury. So you get a sense of the relative size of these planets. Then it lists Jupiter, Saturn, Uranus, and Neptune. We'll be studying these next chapter. This chapter will start now. And you'll see those are enormous compared to Earth, Venus, Mars, and the Moon, and Mercury. I keep leaving out Mercury. In fact, the Moon by that time is almost a period on the page. Okay. Then it shows the Sun compared to Jupiter, Saturn, and the other. And by this time, the Earth is like a pixel on the page. I mean, just a little bitty dot, okay? And then it shows some of the bigger stars the sun is not a very big star, about average, and it shows some of the bigger ones with the sun being a real little thing over here. The Earth is you can't even see anymore. Okay, and then it shows galaxies, in relative sizes. It's just a really neat illustration of how vast the objects in the universe can be. Okay, so that's there, and then after that, I think that's about all. So I'll get the PowerPoints up there, not tonight, possibly tomorrow, or possibly sometime over the holiday weekend. Maybe, hopefully, knock on wood. If we have to go out of town, I may not have internet access, so we'll see. Okay. Yeah, so that pretty much sums it up. So to review what we did in class last time, go to the YouTube video. To hear me talk about the syllabus and safety and research paper and other things, go to that first one, the one that says syllabus. That's near the top. The one for chapter 14 is at the bottom. Okay. This one will be underneath that one, and it'll keep going. Okay. Any questions on what we're doing, what we've done already, what we're going to be doing, how today's going to pan out? Okay? Then let's get started on chapter 15. Let me review, and just in case you didn't catch it. Chapter 14, the title was The Universe. Okay, we started big. Everything. Okay? We talked about stars and how stars form and how stars live and how stars do all the things that stars do. Then we talked about groups of stars, binary stars, star clusters, galaxies, and then clusters of galaxies. So we talked about all sorts of stuff there. Now we're narrowing down a little bit. Rather than the whole universe, we're just going to look at our solar system. That's our sun and the planets that are around our sun, the dwarf planets that are around our sun, the comets that are around our sun, the asteroids that are around our sun, everything. By the way, solar means sun. Sol is sun. This is our sun system. Now that picture right there is one of the planets. And right now, on first glance, I would say it was Jupiter, but I don't believe it is. Because Jupiter has what they call the great red spot that looks like this, but this is a blue spot. So I'm about to guess that's probably Neptune or Uranus, but I'm not absolutely certain on that. It's just a neat picture anyway. Okay? Here is the core concept for this chapter. And this is located on the first page of the chapter. By the way, the books, I see most people have books. The solar system is composed of the sun, that's Sol in the solar system, and the orbiting planets. Okay? We have 8 planets we know about now. We used to have 9, we said, but they reclassified Pluto to be a dwarf planet. And there's some other dwarf planets too, so we'll talk about those. And then the small solar system bodies, which includes, I mentioned asteroids, I mentioned comets, but I forgot to mention meteors. Meteors are out there as well. And then something I didn't mention too was moons. Mercury has no moon, Venus has no moon, Earth has a moon. Now Earth is the 4th of the smallest of the planets, okay? And yet we have one of the bigger moons in the solar system. Now there is, or we think there's a reason for that, theoretical anyway. It's a really big moon for the size of us, this Earth. Mars has 2 moons, but those 2 moons are tiny compared to our moon. Then there's the asteroid belt, and then there's Jupiter, the biggest planet in the solar system, by far, okay? And it has literally dozens and dozens of moons. I'm not even sure everybody has a good count on it. It seems like it may be in the 70s, 50s or 70s, somewhere way up there. Lots of moons. Several of them larger than our moons. About 2 of them much bigger than our moon. 2 of them about the same size as our moon. Some of its moons are actually larger than the planet Mercury. Okay, big planet, big moons. Then comes Saturn, which is a good sized planet, but not nearly as big as Jupiter. it has some interesting characteristics. Number one, it's beautiful rings. But number two, it has a bunch of moons too. Now, not as many as Jupiter, okay, but some of them are almost as big as those in Jupiter. Titan is one of Saturn's moons, and it has another one that I think are both bigger than our moon, and I think one of them may be even bigger than Mercury still, okay. So it has several. And then we have Uranus, which has quite a few moons, and Neptune, who has quite a few moons. Now, we probably don't know everything about these last two because those are so stinking far out there, we hardly know anything about it. Now, a very interesting thing, I think it's interesting anyway. I bet you none of us have ever seen Uranus or Saturn, or Neptune, okay? We may not have seen Saturn to know it was Saturn, but we've seen enough pictures of Saturn, okay? But even with the best set of binoculars you can buy, you can see Saturn. I don't think you can see the other two.
What about like a really good telescope?
What's that?
Would you be able to see them with a really good telescope?
With a very, very, very good, powerful telescope, yes, you can, okay? It takes that, okay? But then they still aren't very distinct. What pictures, ideas we have of them are from spacecraft that have gone relatively close to them, because even the best telescope can't give us very much detail. Now, while I'm saying all this, that used to be the ninth planet, Pluto, which is no longer counted as a planet. So many things just didn't fit. These were all giants out here, so much bigger than these four, yet Pluto was smaller than Mercury, I think. So it just didn't fit size-wise. It didn't fit constitution-wise. These are all what they call gas giants. They don't have a solid surface. They're gaseous, you know, the gaseous surface, okay, unless some of those gases are frozen or something like that. But I think they're all gas giants. That's what we call them anyway.
So, what do they call gas giants? Are they considered planets still?
What's that?
Are they still considered planets?
I can't hear you.
Are they still considered planets?
Oh, they're planets, for sure. But they're mostly gases, not solid. Their core may be solid, so somewhere down there may be solid, but they're mostly, you know, just giant balls, very dense gas, but, you know, but they are planets, okay? Pluto, however, is rocky, just like the inner four, except it's not really very much like us either. So it just doesn't fit. And the other thing is, all these eight and the asteroids are all in sort of a plane that goes around the sun, you know, a flat disk. Pluto is like this. It's not in that disk. So that's why they call it a dwarf planet. One of many reasons. Okay, now, the other small system bodies. Then the dwarf planets, then we have the asteroids are in here, the comets are all over the place, way out usually, and then the meteors are all over the place. Okay, so that's basically the solar system. So looking at 15.1, planets, moons, and other bodies. Now, who determines what's what it's called, what it's named, all these things, is the International Astronomical Union, the IAU. It's the governing authority over the names of the celestial bodies. So that's how they get named. Even features on them are named. For instance, different craters on the moon are named certain things. International Astronomical Union helps determine that. The names of those various moons around Jupiter and Saturn and the other, those that have names, they help determine those names. I imagine they help determine names of stars too, you know, and galaxies or other things. So they're honchos. Okay? Now this IAU, International Astronomical Union, defines what is a planet and what's not a planet, what's a dwarf planet and what's not, and these other small solar system bodies. They're the guys back in 2003 that decided Pluto just did not fit enough of the criteria of a planet to be classified a planet. I've given you several of those already. One of the main is that it's just not in the same plane that we are. The others are within a fairly thin disk going around the sun, and it's at an angle of about 17 degrees. So it's really bizarre how different Pluto is. So it's been redefined as a dwarf planet according to those IAU definitions. Basically what they did, they refined the definitions in that throughout Pluto. Now, before we go too much here, I guess this is okay. I just wanted to make sure I don't skip over something here, but I believe we're still, yeah, let's hit it now. Here's a better listing here. Again, what's our solar system? The main thing is the sun. Now, when I say the main thing is the sun, I really mean the main thing is the sun. I want to read you a sentence from your text. Not everybody has a text, but I want you to be sure you gather this one. Okay? Now, I see something, a contradiction right here. Let's go back a slide. In our book, it says, at the August 24, 2006 meeting, this says 2003, the definitions of planets, a dwarf planet, small solar system, were clarified and approved. And it sort of indicates to me, no, I think they got something messed up. 2003 was when they found another dwarf planet, okay? So the 2003, that should be 2006 for Pluto, I'm pretty sure, okay? We'll come back to that in a minute. I don't know. The date's not really important, but I just noticed the contradiction there. Okay, but here's the sentence I wanted to read from the text. I know it's in here. Here it is. The sun has 700 times the mass of all the planets, all the planets' moons, all the minor members, the dwarf planets, the asteroids, the comets, the icy bodies, everything else put together. Everything else put together, the sun is more than 700 times bigger than all that put together. So when we say the main thing in our solar system is the sun, we mean it. I mean, yes.
How do you know that? Because every time they send something to the sun, it burns up.
Okay. You said, how do we know it? And what's the last
Yeah,
one?
because anything gets close to the sun, it burns up. I mean, just
Okay, yeah, we only count things that haven't burned up in the sun. Mercury being about the closest, okay? Everything else we can measure and stuff like that. And the sun is enormous compared to everything else. Now, Jupiter's big, but it's not nearly as big as the sun. Okay. Now, the one reason I point this out to you, there is another sentence on the slideshow coming up toward the end of the chapter that seems like it contradicts that. They left off a phrase that needs to be put in there. And that's why I'm making a big deal about it now. Sun is huge compared to everything else. All right. Then we have the 8 planets, and they go Mercury, Venus, Earth, Mars. And we have the asteroid belts, that's right in there. Then we have Jupiter, Saturn, Uranus, and Neptune. Those are the 8 planets. Oh, and here's what I was starting to say before. When I was saying how far out Uranus and Neptune are, you've never seen them with a really, really, really strong, powerful telescope. Yeah, maybe you can see them, and then very vaguely. Well, guess what? There may be another planet out there, or 2, that we haven't even detected yet, because it's so far away. Now, believe it or not, there's a lot of evidence there is one, but we've never seen it. What's that evidence? Gravity. We can tell it affects other things around there. Something is affecting that in a weird way, and it could be accounted for by a big planet somewhere out there. But it's just so far away, we don't know about it yet. So that's why I say we know of 8 planets. And when I'm not even talking about Pluto, I'm talking about there's something else probably out there, maybe another planet. All right. Now, this is probably a good time to do it. They say approximately 100 moons that we know of, okay? Like I said, more than half of this is already accounted for by Jupiter. Saturn has an awful lot. We know that Uranus and Neptune have several. We probably don't know exactly how many. So there's, I'd say, well over 100 moons out there. Depends on how big you classify a moon. Next, thousands of asteroids. Those are in that belt between Mars and Jupiter. Millions of icy bodies out there just floating around. Some of those are comets, okay? So there's tons of things out there. Now, what this list did not include, and this PowerPoint is from an older text, I want to now, at this point, mention the dwarf planets, okay? And the reason is your book mentions them now, even though the slide set doesn't. So let me read this. And this is where I think some of the contradictions with the dates came into place. The old definition of a planet, back when Pluto was counted a planet, was any large, somewhat spherical object that orbits the sun. And that meant Jupiter was included. Pluto was included. And Melanie's included. Okay, good. All right. Because it was basically spherical and it orbited the sun. Most of the smaller things aren't perfectly spherical or even close to it. But Pluto was, so they counted it a planet. Okay. But then in 2003, this is where the 2003 got mixed up, I think, a new astronomical body was discovered. That body was named Eris, E-R-I-S, after the Greek goddess of discord. Okay. Eris caused problems because once they found her, that then said, well, we either got to count her as a planet or declassified Pluto. So Eris was round, more massive than Pluto, so it was spherical. It circled the sun. Was it a planet? Well, if it was, okay, then that meant Ceres might be. Ceres was one of the perhaps 50 or so icy bodies believed to be orbiting the sun far beyond Pluto. Yeah, what a bag of worms we got. Okay, so the idea of 50 or 60 planets in the solar system said, hey, no, we can't count all these other things. They don't fit many things, but they fit as many as Pluto does, so let's just throw that whole mass of them into being dwarf planets, or maybe not all of them. So when so that came about. Today there are 8 planets, as mentioned here. What they don't mention here, at least 5 dwarf planets. Okay? Pluto being one, Eris being another, Ceres, that icy one way out there, was one, and then these 2. Makemake, believe it or not, that's its name, and Haumea. Now, frankly, they sound like Hawaiian names to me, but I don't think they have anything to do with Hawaii. Okay? And then there's many, many small solar system bodies. So right now we know of 5 dwarf planets. Probably more, but we know of 5. Pluto, Eris, Ceres, Makemake, and Haumea. Just for future reference. I think this slide should have had it. They just left them off. Okay? Now, let's get back here. What is an astronomical unit? Well, it's something...
It's the distance between Earth and the Sun.
Earth and the Sun, exactly. The average Earth-Sun distance, that's about 93 million miles, which would be about 1.5 times 10 to the 8 kilometers. That would be 150 million kilometers, approximately. Okay, now, why have an astronomical unit? Well, in the last class we talked about when you're talking about stars and galaxies and stuff, you talk about light years, because no distance measurement we use is anywhere close, and even then, just across our galaxy is 100,000 light years. It's huge, okay? Now, when you're talking things with the solar system, you don't want to talk about light years because it's nowhere close to the distance of a light year. But if you're just talking in miles and kilometers, you see you got such big numbers. So to use something in between, we use an astronomical unit, which is the average Earth-Sun distance, okay? 93 million miles. It's a pretty big number, and we'll talk about in terms of that. Now, we classify our planets several ways. One is by size, and we're going to talk about them here. Density, we're going to talk about that a little bit too. That's also in there. Atmospheres, yeah, that's important, okay? And what they sort of left off was constituent. What are they made of, okay? That's part of density, but that's not all of it. So the first classification then are these two. The terrestrial planets, terrestrial meaning rocky, okay, and the giant planets, and usually that has another term with it, gas giants, meaning not rocky, not solid. The surface is a gas, is a cloud, you know, type of thing. Okay, your terrestrial planets are the interior planets, Mercury, Venus, Earth, and Mars, in that order from the sun. Oh, I meant to say this too. Let me go back a slide or two. Will you ever see the planets lined up like that? Absolutely not. This is just an illustration just so you can see the 8 planets. They're never stacked up in a row like that, ever, anywhere close to it. That's one problem with this picture. Another problem with this picture, and if you go to that Space Objects in Perspective, you'll see what I'm talking about. If this were the size, real size of the sun, you wouldn't see any of the planets. They would be so tiny you couldn't see them. But if these were the planets, the relative sizes are probably not too far off. But if they were on here with the sun would be, you couldn't fit it on the page, okay, because it would be so incredibly large. And then the one other thing that's really wacko about this picture, the planets never line up like this. The relative size of sun to planets are way off. The relative distances are wacko too. This makes it look like all the planets are about the same. Maybe these a little further apart. When we get to talking about them, we'll see nowhere close. The inner planets are relatively close, but then the outer planets get so much further away. I mean, sometimes almost doubling the distance than the other planet was. I mean, it's just incredibly big. So this picture is just qualitative, definitely not quantitative. The relative size of the planets are close, but that's about all. And sort of the little moons are fairly close. Okay. So, sorry, I just happened to think about it. So, let's look at the terrestrial planets, the inner 4. Mostly rocky materials. And most of that rock is metallic, nickel, and iron. They really should say it the other way, iron and nickel. Iron's the most prevalent metal in our solar system. Metal in our solar system. Okay? Just about every object in our solar system has a lot of iron in its core. We are mostly iron in our core. Okay? We don't have that much at the surface, but we have a lot inside. Okay? Then the giant planets, often called gas giants, Jupiter, Saturn, Uranus, and Neptune, they're mostly hydrogen, which is a gas. Helium, which is a gas. Methane, which most of the time is a gas. Now, when methane is cold enough, and some of these planets are quite cold, it may turn into a liquid or possibly even ice, methane, solid methane. Okay. Pluto, no longer considered a planet, now a dwarf planet, along with Ceres, Eris, Makemake, Haumea, and which was the one I left out? The icy one. C. What was that? Ceres, I said. Oh yeah, I guess I got them all. I just didn't. I wasn't counting Pluto. That was the picture. Okay. Yeah, we got them all. Okay. And again, faulty picture here, just giving you, and like I said, relative sizes, not bad. Mercury certainly the smallest. Mars is bigger than Mercury, but not a lot bigger. Venus and Earth almost the same size. Jupiter much, much, much bigger. Saturn not too far behind Jupiter, but still much smaller. These two almost the same. Now this picture is not a good one because it lists Pluto, and Pluto shouldn't be there. Here's another reason Pluto shouldn't be there. All the others are in, none of them are in circular orbits, close to being circular orbits. They're elliptical orbits, but their degree of being ellipses is pretty small. They're really close to being circles, except for Pluto. Pluto is much more elliptical. In fact, for a fraction of the time, Pluto is actually inside Neptune. It's closer to the sun at some point and much further to the sun to the other point. Okay. Now, not a lot closer, but just a little bit. Every now and then, Pluto's orbit comes inside the Neptune, but most of the time it's way outside. So its average distance is here. It's off here, yes.
All right. So you said Pluto goes around Neptune sometimes?
It doesn't go around. It goes around the sun, but, okay. I'm going to try to do this. Let's say, okay, Patel, you're the sun today. You're right? Okay. All right. He's the sun. Now, got your name. Thomas, yeah. I know.
Mike.
Yeah, okay. Okay. If he's circling around Patel, okay, and then, let's say, I can see it like having Corey, right? Okay, Corey is circling around this one. And then out here is Michaela circling around. So those are the first three. Okay. All right. Well, then somewhere out here, Neptune. Can you be Neptune for right now? Okay. The relative distances are not good. So she's Neptune going around. Furthest one out. Okay. Pluto, most of the time, is somewhere way out there. Now, Neptune, when she goes around, she's going to bump into this wall and go into that wall. I mean, she's going to do here. But Pluto, most of the time, is way, 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 way out there. But every now and then, it'll come just inside Neptune. Uranus is here, Neptune's there. Comes inside, but then it goes back out again. So that's what I mean, elliptical orbit. It's not anywhere close to circular. It's elliptical. Most of the time, way out there, but every now and then. You know, this is what the comets do. The comets live way, 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 way out there, but every now and then come down and come close to the sun and then go right back. Okay. It takes them hundreds of years to do that, but they do. Some of them thousands of years to do that. Okay. Well, Pluto acts more like a comet than any of the other planets do. So there's another reason it's not really good to call it a planet. It's a dwarf planet. But again, the relative distances here are bad, and the sun to planet, I mean, this makes it look like the sun is maybe just 2 or 3 times bigger than Jupiter is that. Nowhere close. The sun is 700 times more massive than all the rest of them put together. Everything you see there and much, much, much more.
So let's put everything towards the sun.
What's that?
Let's put in all the planets towards the sun.
The sun's gravitational field. Okay. Just like, why do we, can you jump up and leave the Earth? No, the Earth's gravity is pulling you down. Well, that's nothing compared to the sun's gravity. That's keeping everything in our solar system is influenced by the sun's gravity. Even those icy bodies that are literally, those are light years away, okay? They're still getting pulled in. Yeah, what's that?
So it's something about that sun, huh?
Yeah, the sun is, that's why we're called the solar system, her system, Sol's system. Okay, so let's start with the planets. But before we do, okay, there is a figure in your book That's a lot better than this one was. But it's still not up to snuff here, okay? But it is a lot better, okay? I can't hold it here long because it's just too heavy. Again, the relative sizes of the planets are not far off from being what they should be. Now the sun is probably better proportional, but I still think it's way too small compared to the other, but it's much bigger than this would indicate. Now these show these fairly close, and they are, but they do separate more the further you get out. These show that they're pretty uniform. They don't. They separate more the further you go out. Okay? This one does show that Ceres is one of the asteroids, but it's spherical and, you know, big enough to be considered a dwarf planet. Pluto out here just beyond Neptune, Haumea out beyond it, Makemake beyond it, and somewhere way out there is Eris, which is bigger, I think, than all the other dwarf planets. Okay? But it's not big enough to be counted as a planet. Okay? So that's a little bit better picture, but still not accurate. Okay? But they can't make it perfectly accurate and make it fit on the page. It just wouldn't work. The inner ones would be so close together you couldn't distinguish, and the outer ones would be so far apart, too much space would be taken. There is an example here, and just like in the first chapter, we're not going to do these examples unless there's something that's useful to you here. And this is just a question. How long would it take to travel the average distance between the sun and the earth at a typical jet airplane speed of 1,000 kilometers per hour? That would be about 600 miles per hour. Okay? And they're using equations from 2.2. Well, we didn't do chapter 2, so that's why I don't feel like I ought to require you to do these exercises. But if you look at their answer here, boy, it takes a while. They come out with about 2 months of traveling. Okay? Now, what was that again? The distance between the Earth and the Sun at a typical jet airplane speed. Around 2 months. Okay? Actually, they said can make that must follow a curved path requiring a much longer trip. So that's if the spacecraft traveled at the 600 miles per hour, which sounds pretty fast. It would take you more than 2 months to get to the sun. Not that you want to go to the sun. You, as you said, somebody said, yeah, it would burn up. Okay, so you're not going to go there. But if you could, it would take you more than 2 months to get there at the fastest jet plane we have. Okay, that's how far we're talking. And of course, you'd have to refuel many times in that, and there's no place to refuel there either. So it's all speculative. But there's the thing. Now, there is example 15.2. Interplanetary space probes travel about 7.3 kilometers per second. That would be 10, 11 or so miles per second, which is pretty fast. How far could it travel in a year? And they say about 2.2, let's see, what is it? 230 million kilometers. Okay? Oh. I find that hard to believe. I think they got something wrong there. They needed a few more zeros there, like maybe 18 or something kilometers. Okay. But we won't go there. That one wasn't worth reading. Okay. Now, before we hit the tables, I mean the planets, there is a table here which is, to me, one of the most fascinating things in the whole chapter. Now, much of the stuff from here will show up in other places, but this is worth studying by itself, okay? And just a few of the things here. It lists all 8 of the planets here. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Okay? It has average distance from the sun, and if you see by this, you'll see those figures we had aren't anywhere close. And they give it both in millions of kilometers and in astronomical units. Of course, the astronomical unit for Earth is 1. That's 1 astronomical unit. That's how this is for Earth. Okay. Inclination to the ecliptic. That's that thing I was talking about. We're in sort of a fat pancake. Well, the inclination, the ecliptic is the path that the Earth goes around the sun. That's what the ecliptic is. And some of these are up or down from that. And that's what these degrees are. Now, of course, the innermost planets, like Mercury, will be greater degree. They're not that far out of line, but they're so close it makes the degree greater. You see Venus is 3.4. They keep decreasing until they get to Saturn, which is a bit further out. But well, those out there, you know, they're all within a very small range. If you included Pluto, Pluto would be something like 15 to 17, 18, 20, something like that. Way out of line with everything else, okay? Orbital period. Now this is measured in Earth years, okay? And you'll see that the ones closer to the sun move much faster, further from the sun than the Earth move much slower. Rotational period, that's how the spinning on the axis. Orbiting is going around the sun. Rotation is spinning around the axis, their axis. And Earth in days, okay? And then it also has minutes and seconds. The mass with the Earth being 1, how many times? And you see that Mercury is incredibly tiny compared to Earth. Venus is almost the same size. Mars is surprisingly small compared to Earth. The others, much, 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 much bigger mass-wise. Okay? Now, equatorial dimensions, this is in diameter in kilometers, but then also with Earth radius is 1, then you compare, and you see that Mercury, even though it's quite a bit less massive, its diameter is only, you know, about 3/8 that of the Earth. So it's much, you know, big. Venus, almost the Earth. Earth is the Earth. Mars, about half that of the Earth, a little more than that. But then you get to the big ones, and they're many times larger. Okay? I can't hold that up much longer. To me, the most interesting of these, and they said it here, oops, on the last slide. Oh, yeah. Let me go back here. And they're saying classification by density. Okay? By density, if you look at the inner 4 planets, 5.43, 5.25, 5.52, and 3.95. Mars is a little out of kilter there. But look at those. They're all basically 4 or higher. Mars is just under 4. You go to the gas giants, and they are less than 2. So big differences in density. So that's another classification thing. Atmosphere, it gives either Mercury has none, and the others it gives what the constituents of the atmosphere are. Notice the only one with oxygen. Earth, okay? We couldn't exist on any other planet in our system. There's not enough oxygen there for us to breathe. We've got to breathe oxygen. Nor is there enough for plants to live. Nothing could live there. Okay? Now, I'm not saying this for all planets out there in the universe, but certainly in our solar system, we're the only one close. Okay? And then solar energy received, and this is just basically how close you are to the sun. Mercury is the most, and Neptune almost 0. I mean, it's so incredibly tiny. So that one's not really all that interesting. But the table itself, fascinating, the data. Now, when you go back to density, what do you notice? What is the densest of the planets? Looking at the table. The one with the greatest density, greatest mass per unit volume. Earth! Now, not by a long shot, but it's still the Earth. Mercury is actually second, then Venus, then Mars. The gas giant's way out there. Something so bizarre, we'll talk about this later. Saturn, notice its density is less than 1. What does that mean? If you had a pool of water big enough, which nobody does, okay, Saturn would float. It wouldn't sink. All the other planets would sink. Saturn wouldn't. It's less dense than water, okay? The least of the density of the planets. All right. Fascinating table. Much of what we're going to talk about each of the planets will tie into that table, okay? But that table puts it all in one place. So Mercury, innermost planet. The planet closest to the sun. Now remember I said most of the planets have fairly close to a circular orbit, but none of them are circular. Most of them are slightly elliptical. All of them are elliptical. Mercury, except for Pluto now, because it's no longer a planet, is a highly elliptical orbit. Well, part of that is it's so close to the sun. The sun is one focus of that ellipse, the other one being a little further away, has to be a little more elliptical. The average distance from the sun is about 4/10 of an astronomical unit. What's an astronomical unit? If this is the sun, if this is the sun right here, and this is the Earth here, that's 1 astronomical unit. So let me get on here. This is the sun, and that's the Earth. That's 1 astronomical unit. 4/10 would be about here. So Mercury is very close to the sun, closer to the sun than it is to Earth. Okay? But not by much. Its orbital period, how long does it take to go around the sun? It's so close, it doesn't take that long. About 3 months, about 1 season for us. January, February, March. It's going around the sun 1 complete time before we do a quarter of the way. Now, its rotational period, though, is 59 days. That's almost 2 months. So it takes 3 months to go around the sun, only 2 months. It takes a full 2 months for it to spin once. So therefore, it's not spinning very fast, but it's going around the sun really fast. Okay? So it has a rather strange... Every day and a half on Mercury is a year. Their year, not our year. I'm sorry. Yeah. Wait, I didn't say that right. Yeah, that's right. Every day and a half, that would be a rotational period would be, it takes 2 of our months for it to go to spin 1 time. That's their day. And it takes 3 of our months for it to be a year, their year. Okay. Now, have we ever seen Mercury? Well, yeah, some people have. I haven't. I knew what I was looking at. The thing is, you want to be the sun again? Okay. So you're the sun again. Now, if you were to hold, I have a real good memory. It's just short. Michael, okay. If Michael were Mercury, okay, then where I'm standing now would be about Earth. Because you're 4/10 the distance from here. Okay. Now, a lot of time Michael would be behind the sun. I'll never see Mercury because it's on the other side of the sun. If it's on this side of the sun, I'll never see Mercury because it's tiny compared to the sun. The only time that I could ever see Michael is right about where he's sitting now, and when the sun is just coming up. You see, most of the time, okay, in the daytime we'll never see Mercury. The sun's too bright. We'll never see it in the daytime. At night, we'll never see Mercury because it's close to the sun, and the sun is somewhere on the other side of us, okay, in our night. We're facing this way, it's there. And so is Michael, okay. It's only right when the sun's coming up or right when the sun's setting, and Michael is located right about where he is now, we might get a glimpse of Mercury. Just a glimpse. Only for a few minutes, probably. Because soon the sun's up and too bright, or it's down and it drug Mercury with it, you know. you just aren't going to see Mercury much. Okay? Visible shortly after sunset or before sunrise, but only on certain days. That would be only on the days when it's not behind the sun or directly in line with the sun. Then you'll never see it. Okay, now, they really should have put these two things in different order. It has almost no atmosphere. They say no atmosphere. Okay? Now, there's probably two reasons for that. Toward the end of the chapter, we're going to talk about how they think the solar system was formed. And basically, if you remember from the last chapter, how a star is born, not the movie, but how a star is born is when a bunch of gas is pushed together and then gravitational collapse, it gets so hot, then fusion starts happening, you get all that stuff. Listen to the previous slide, you'll hear all that. Okay, now that process of forming the star, though, when nuclear fusion does begin, there are explosions and contractions and explosions. It has to reach that dynamical equilibrium. So stuff gets spewed out and then drawn back in, stuff like this. Well, whenever Mercury solidified then, the sun was probably still sort of unstable. So more than likely it blew the atmosphere completely off, okay, in the process. Because atmospheres are mostly gases, okay? The other thing is, if any remain, they may have got sucked into the sun, just like Michael was saying earlier. Too close to the sun, you lose it. So Mercury has almost no atmosphere. So therefore, all these other bodies that are getting sucked toward the sun, if they happen to get in Mercury's path, or Mercury gets in their path, bang, there's a collision. So therefore you have craters. Craters like crazy because there's no atmosphere. Why? We get bombarded with meteors all the time. Most of them never make it to the Earth. Why?
Gravitational force.
The what?
Gravitational force.
One more time.
Gravitational force.
Gravitational force, that's what's pulling them to the Earth. But why don't they make it to the Earth?
Because the friction burns you.
They burn up, exactly. Because our atmosphere is a relatively dense atmosphere. They burn up somewhere in the atmosphere because of the friction. They're going so fast, believe it or not, our atmosphere is so fast the friction is enough to burn. That's what we have two names for them. Anyone know those names? For meteors coming toward the Earth. When we see them at night, we call them either. Say again? Shooting stars or falling stars. Catch a falling star and put it in. No, that's way too late. Okay. Now, that's what we call them because they're burning up as they come through the atmosphere. However, some of them have hit the surface and may have made little craters, but not much. Mercury, no atmosphere at all to block them, so therefore, sorry. Here's that first picture. Now, this is greatly exaggerated, but if here's Earth, Mercury is going around the sun, and see, the sun is huge and Mercury is minuscule. So this is greatly exaggerated. But the only time you would see it, if it's too far back here, you're not going to see it. If it's too far here, you're not going to see it. If it's out here, but it's anywhere over there, you're not going to see it, okay? Only when it's somewhere here. Now there is the brightest one, that we call that a full Mercury. But it's on the opposite side of the sun, so it's even further away, but it's so close to the sun, you're not going to see it. It's only when it gets out here, you'll see less and less of it because you see only the part toward the sun is being illuminated, so this is not. So here you have basically just a sliver of Mercury when it's closest to us, some of the closer distance, and most of it's facing the sun, so it's black. You're not going to see it then either. So it's really, really hard to see. Only for a few minutes before and after sunrise, that's the only chance you got. Okay? And then only certain times would it even be possible. Okay? It is, by far, the smallest of the planets. a fair amount. Well, Mars is close to it, but not that close. Okay? But here is a picture of it. And now this is a composite picture of several pictures. You can sort of see the scenes where they put them together. But every one of these little spots here is a crater. And craters on craters on craters on craters on craters. It is just pockmarked because of all the stuff that hits it, because nothing is going to burn up in its atmosphere because it has no atmosphere. Okay? And it's definitely the smallest planet. Okay. Now, before we move on, would you say it's the hottest planet?
Mercury?
Yeah. Why not? It was guessing well, but it's closest to the sun. You would figure it's the hottest planet. Well, I guarantee you this, okay? You're going to be the sun for us again, right? Okay? My hand's going to be Mercury. Okay? Now, you got an idea. This half of Mercury is hotter than blazes. This half is frozen for that moment because there's no sunlight hitting it. Okay? Now, it turns very slowly, but on average, the side toward the sun is burning hot, and the side away from the sun is incredibly cold because it has no atmosphere to balance out. Okay? So its average temperature is less than another planet. Its temperature when it's facing the sun is much hotter than anything you can imagine. Okay? So yeah, it is the hottest in spots, but it's not so hot on the other side. Okay? Its average temperature is not as hot as Venus. Now, let's go back. If this is the sun, and this is the Earth, remember, Mercury was about here, 4/10 of the distance. Venus is about here, 7/10 of the distance. It's our closest planetary neighbor by far. Okay, only 3/10 of an astronomical unit from us. So therefore, except for the sun, of course, and the moon, it's the brightest thing in the sky. You won't see it every evening. You won't see it every morning. But on those mornings and evenings you do see it, it's the first thing you see other than the sun and moon. The first one you see at night, the last one you see in the morning. It's the last one to go. It's called the morning or the evening star. But guess what? It's not a star, it's a planet. Okay? But it looks like a star, and it looks like the brightest one in the sky when it's up. Okay? It also exhibits phases just like our moon does, because sometimes, okay, it's going to be the sun again. If you're the sun and now Earth and Venus is over here, then only this part of Venus is being lighted. This part is dark, just like our crescent moons. Okay? When it's back there on the other side, can you be Venus this time? And like this, but not in line with the sun, I see a full Venus because all of the side of you is facing the sun, is lit, and I see a full Venus. When Venus is over here, exactly in between me and the sun, then I see almost nothing because I see the dark side of Venus, which doesn't, you can't see that. It's only when it's there. But, okay. Now, there are some times when, and then too, because Venus is closer to the sun than we are, when the sun goes down, Venus goes down. When the sun comes up, Venus is up. So there's big portions of the morning. Okay. On mornings when Venus is visible, it's not visible at night. And on evenings when Venus is visible, it's not visible in the morning. Because it's on the, it depends on which side of the sun it's on. That's when we'll see it. Okay. So, brightest star in the sky, that's one. It's our closest neighbor. That's one superlative, the closest one to us, of the planets, now, not the moon. Okay? It's the brightest thing we see outside of the sun and moon. So that's another superlative. Okay? It exhibits phases like the moon does. Now here's another thing that is incredibly bizarre. All but one other planet slightly but Venus is much worse. All the ones, okay, let's just say, I think I'm doing right now, that we're rotating around the sun like this. I mean, revolving around the sun like this. We also spin like this. Our rotation and our spin axis are the same. Venus is backward. When it's rotating around the sun, it's spinning the opposite direction. So that means the sun comes up in the west and goes down in the east on Venus because it's spinning backwards. Every other planet, except one. There's one other that does weird things. Okay, but it's the worst. Now here is the other one. The Venusian day, the time of one spin, even though it's spinning backwards, is longer than the Venusian year. In other words, it's going around the sun. It takes less time to go around the sun than it does to spin one time. That's bizarre. Okay? Very bizarre. Now, because it is our closest neighbor, as a planet anyway, we have sent many probes out to Venus. And these are usually called Venera or something that you can almost see Venus in the name. But even those that the purpose hasn't been to go by Venus, they still go by it when they're going somewhere else. So it's been photographed and studied by numerous probes. Now, here's the next thing. It's mostly a carbon dioxide atmosphere. Okay? Now, here on Earth, when I think carbon dioxide, I think that's what we breathe out. But guess what? Carbon dioxide can come from other sources. Venus has nobody breathing out, ever. Okay? It doesn't have things burning, so it just has a naturally carbon dioxide atmosphere. Okay? It is a dense atmosphere. High temperatures because it's closer to the sun, and incredibly high pressures because it's such a dense atmosphere. We could not live on Venus. Number one, we couldn't breathe. Number two, we'd burn up. Number three, we'd be crushed. Okay? Take your pick. Okay? Which do you want? None. And who said women are Venus? No, I didn't say that, did I? Okay. There was a book by that title. And women are from Venus, men are from Mars. That's just the title. Okay. The surface is mostly flat, but it does have some mountains and volcanoes and other things in it. Okay. It does have some variation. So, several weird things about Venus. Brightest, it's closest to us. Brightest, those aren't weird, but they're the closest, okay? Rotational motion, opposite orbital motion, very strange. That means it spins backwards. Venusian day is longer than Venusian year. Totally strange. No other planet does that. And very hot. Now, why is it very hot? Number one, it's close to the sun. But notice what its atmosphere is. What do we call carbon dioxide in our atmosphere? It and other things are called a classification.
Ozone?
Second?
Ozone layer?
No, ozone is O3. That's a different thing, and that's up there, and it's an important layer. But more carbon dioxide in our atmosphere makes us what?
Clouds?
There probably is some connection with that. What I'm looking for is it's a greenhouse gas. What does that mean? It traps heat. So guess what? Venus is close to the sun. It has a very dense, thick, highly concentrated carbon dioxide atmosphere, meaning it traps heat from the sun. And it's so close to the sun, it's so hot and so dense. Even though it spins very slowly, it goes around actually the sun faster than it spins, it doesn't matter. It's always hot. Its atmosphere does not lose heat back to the solar system, back to space. It traps it and keeps it. It is on average hotter than Mercury. Not on degree. When Mercury's facing the sun, it's hotter than Venus. When Mercury's not facing the sun, the other half of Mercury is much colder than Venus. So therefore, And it has no atmosphere to trap the temperature and keep it moderated. So Venus is, on average, the hottest of the planets. Okay. Several features of Venus. Here is, yeah, I'm sure you can read that. These are just some of the probes that have gone toward Venus. Now, I don't know if I'm making this up or if it's really true, but look at who sent most of these. Y'all do know what USSR stands for, don't you?
Yeah, Russia.
Second?
Russia.
Okay. Yeah. Russia was the largest of the United Soviet Socialist Republics. Russia being the biggest one, they were the honcho. Okay. And you notice the last probe was 84. Not long after that, USSR no longer existed. Russia still exists, but the other satellites broke away, no longer part. They sent more than we did. Well, we were in the space race. When they started going to Venus, we decided to go to Mars. You know, we're not going to do anything. And we did share data, and we do. Believe it or not, even though governments may disagree and fight and do all sorts of things, in general, scientists communicate pretty well and share data and share information. So if they were going there, we went to Mars. We did some flybys and stuff like that too. Some of you are not responsible, but if you notice this, Venera, see, Mariner was actually going to Mars, but it went by Venus and did a flyby. I don't know what that says for Venera. These were all primarily Venus. This is another Martian, okay? I think, yeah, that's a Mariner. I can't read these. This was going even beyond any of those, but it's the Pioneers were going further out, but they went by Venus and did flybys, okay? So many of these, the reason was to go there, but many of them, they're just in passing. Magellan, for instance, was on its way to Saturn, I think, but it went by Venus. And Galileo, I'm pretty sure, was going somewhere else and just went by Venus. They all will stop by and see Venus on the way. Okay, here is a computer simulation. No one's been on Venus's surface to take a picture like this, but they have sent down probes and they can tell by the thing. They think this is a huge volcano in the background. Huge volcano in the background. Probably pretty active. It's so hot, you can imagine that it's seismically active. This, they think, are pools of molten rock, okay? Probably came from a volcano, but haven't cooled enough to melt yet. So if they have a river, it's probably molten rock, not a river you want to take a bath in, okay? So yeah, it's a miserable place. Hot. Toxic. In addition to carbon dioxide, it has a lot of sulfuric acid in the atmosphere. Yeah, I want to breathe that. Yeah. No way. Okay. That's Venus. If we go to the planetarium, usually he'll do a pretty good story on Venus. Okay. We're going to skip Earth. That's going to be the next chapter. We'll cover Earth in the next chapter. Let's move on to Mars. Okay. Sun here, Earth here. Mercury here, Venus here. Okay? Sun, Earth, Mars here. More than just about the same distance from, well, okay, let's go back. From Sun to Mercury, more than twice that is Sun to Venus. Okay, now Venus and Earth are fairly close, so that's fine. But then Sun to Earth, Earth to Mars is half that distance from here. So you're getting further and further away every time you go out there. Okay, so that's 1.5 astronomical units. One astronomical unit gets you to Earth's orbit, and then another half an astronomical, half the distance between Earth and Sun that's how much further Mars is beyond Earth. Geologically active regions, okay? Well, they say geologically active and then turn right around and say inactive volcanoes. Now, when they say geologically active, it means it could still be shifting plates around a little bit, but not enough to really create too many active volcanoes. Now, here's a weird feature of Mars. Canyons. What makes canyons on the Earth? When I say canyon, what's the one that pops into your mind? Which one? The Grand Canyon. How did the Grand? Have y'all ever seen it? I've never seen it. I've seen pictures of it. They're incredible. My parents-in-law took one of their grandchildren out to see it, and I mean, they just talked about it so much. It's just incredible. What made the Grand Canyon that huge deep pit there? Anyone know? The Colorado River.
It used to be water, but now it's not water.
Say again?
It used to be water, but now it's not water.
Now, well, water ran through there and ate away the soil. It just kept digging deeper and deeper and deeper. So canyons are usually, canyons as we understand them, are made by water erosion. Whoa! Does that mean at one time there was water on Mars? Probably. Unless something else made those canyons. Okay? Now what's more, we know water is still on Mars, but none that we know of on the surface. It's all ice near the poles. Okay? Now, terraced plateaus near the poles. So at the poles, you have these higher regions, terrace-like. Again, usually you think of caused by water erosion, but maybe not always. That may be the geological activity. Now, there are other flat regions, and here again, they got things out of order. They should have said this first. Thin atmosphere, which means not much to keep meteors out. So therefore, pitted with craters, that means you've just been bombarded with meteors that have hit the surface. We have such a thick, I bet you, I don't know, I've never been there, I bet you Venus doesn't have many craters at all. Because it has a thick, dense atmosphere, everything's going to burn up in that. Most things burn up in hours, okay? Not much burns up in Mars. Too thin of an atmosphere, and guess what it's mostly? Carbon dioxide. So how is this true? Mercury, no atmosphere. Venus, very thick, dense carbon dioxide. Earth. Mars, carbon dioxide. And yet our atmosphere is mostly nitrogen and oxygen. Go figure. How did we get so lucky? You know? Without that, we're dead. We're not going to live. There's no life on this planet if we had the atmosphere of the planet inside or outside of us. That doesn't support life. Okay? Now, I can say strong evidence, those canyons and other things, for liquid water in the past, but we know of no liquid water in the present. Okay? Numerous space probes have gone there. Before we hit the space probes, there's some other evidence of water. Now, this is not, to me, very strong evidence, but it is some. It's hard to tell here. People who know what they're looking at can tell. And this is so hard to say. The shape on one side as opposed to the other, and you'd have to do a lot of studying in this, indicates that more than likely there was some type of erosion, and more than likely that was water erosion. You know, this is a gentle slope here and a pretty steep slope there. It just has all the characteristics of water erosion. Okay. I want to tell you a story of not Mars, obviously. I've never been there. But my wife and I think I mentioned, we went to, no, that was my last class I mentioned. Okay. She had professional meetings near Salt Lake City, and it was right at a term break for me, so I got to go with it. I don't usually get to go, but I got to go this time. And we got there a few days early, and we wanted to see around some of the areas we hadn't seen before. Some that we had, but some that we hadn't. And we went pretty sure it was the Snake River. Now, we'd seen the Snake River back in Yellowstone, or not Yellowstone, Teton National Forest, but we hadn't seen it further up. And when we got there, I started saying to Karen, this doesn't make any sense. Usually when you have water running through an area, at least the banks are slightly tilted. When we saw the Snake River, the banks were just about vertical. I said, what caused this? This isn't how water usually cuts. Even the Grand Canyon, which has some pretty close to vertical, there's still some slope to it. The Snake River didn't. Okay? And what's more, I can't remember the town that we were near, but we didn't go this close to the thing, but when we did go close and look down, I mean, people in rafts looked like ants. It was way, way, way down there, and the walls were almost vertical. Karen, what could have caused this? This doesn't make any sense. Well, a little bit later, we drove around, and then we came to one of the informational signs, and there had been, we'll talk about this in a later chapter, glaciers during the ice ages had come down from Canada and made their way across. And when glaciers go there, I mean, really, really thick sheets of very dense, heavy ice. And they're always moving, not very fast, but moving. And they do what they call bulldozing. And they bulldoze anything in their way up, and it gets caught in the ice, and then it becomes part of the ice, and then it is like sandpaper, you know, you have these rocks and boulders and stuff caught in the ice, and they grind away. Well, all that got pushed ahead and carried along, and then at some point, the weather changed and the glacier started retreating. But it left all that rock and debris up front, and then behind that, they were melting, and it started filling up. Well, it made its own dam, okay? And water filling up, you had the biggest lake, way bigger than Lake Superior, way bigger than any lake probably that I know of. And it had a name, and I can't think of it now. But that dam was made out of chunks of rock that were just sort of piled there together. And sometime, I mean, thousands of years later, I don't know why, but the dam started weakening, and it broke. And this biggest lake that maybe ever existed, started pouring out water, and it went down the Snake River, and it went at such a rapid pace, it took it, I think, more than a week to empty. And it just dug out a channel with vertical sides. That's why. They weren't sloped, they were vertical, because that water was rushing down for long periods of time. I think it was 7 to 9 days, you know, just rushing water going down there. Well, that's not what happened here, but that shows the terrain on one side and the terrain on the other side are very different. And you would think the only way that could happen is if there's water there going through there, eroding away the rock on that side. Now that probably was way more than what I was supposed to get out of that, but that's what it's saying to me. Strong evidence for liquid water in the past. That kind of evidence, that's pretty amazing. Whoa! That's all they have. They don't show a composite of Mars like they did the others. Let me make sure I'm keeping up. I haven't been turning the pages like I should. Now, I thought they had this, and maybe it's going to show up later. Here is a table of the Mars probes, okay? And if you look at these, predominantly U.S. with some USSR, Soviet Union. We call ours Mariner, they call theirs Mars. They went Mars 2 through 7 here, okay? We have Mariner 3 through, goodness gracious, I see a 9 there. I think we started naming ours something else later. So those are the probes that went to Mars. Maybe not quite as many as went to Venus, because Venus is closer, and even when we went to Mars, we sometimes went by Venus, because the Mariner probes went by that. The Venusian probes did not go by Mars, because you hit Venus before you hit Mars. Okay. Now, while we're here, might as well do it, since the picture is here. Here is, and this is on the slide set, so I wanted to show it. These are size comparison for the rocky planets. What's the other word for that? Terrestrial planets. Mercury, look how small Mercury is. Venus, Earth, this is almost the same size as Earth. Not as dense, but almost the same size. And then Mars. Mars. Now, weird thing is, look how big our moon is. I mean, comparable to the size of Mercury. Smaller, but comparable. There's one of Mars' moons, probably its larger moon. Look at the difference there, folks. I mean, just enormous. Okay. Now, maybe this is a good time. Oh, no, I'm sorry. That's not Mars' moon. That is the dwarf planet Ceres. Okay. And that's in the, isn't that the one in the asteroid belt? So they just show that. That's why it's called a dwarf planet. Look how small that is compared to the other. Okay. Now, maybe this is a good time to say this. Maybe it's not the best time, but it's one. Why does Venus turn backwards? Nobody knows for sure. But a theory that seems to be supported by other evidence is that perhaps Venus had an enormous collision. Now, this would have been way back in its history, maybe shortly after the sun was forming and throwing out things and everything getting messed up and stuff, that Venus may have gotten a huge collision with something, some other object, an asteroid, a chunk of something, and it knocked Venus so hard that it actually made it turn in the opposite direction. That's the theory, a theory. Now, why is our moon so big compared to the size of Earth? And there's some other features. We'll do this in a later chapter. But the theory is Earth got hit by something really, really big and probably broke off a chunk of Earth. Now, this is back when Earth was probably still molten. This is shortly after it was formed from the sun, and so it wasn't a solid yet. It was still molten, got hit, and part of it went out, and it was a big enough part, it became spherical, and that was our moon. And there's several bits of evidence that suggest that's probably what happened. Okay? Strange but true. Well, if that happened to Earth, it could have happened to Venus too, only it made it turn the other way. Because Mercury doesn't have a moon, Venus doesn't have a moon, Earth has one, but it may be a chunk of itself. Mars, that's so close to the asteroid belt, it may have picked up a couple of little asteroids. Maybe that we all originally didn't have moons, but then something happened that Mercury and Venus still don't. Okay, that's speculation. Okay, so that was Mars. Okay, now here is a couple more examples. I don't know if these are worth looking at. If the noontime surface of Mars can reach a high of 20 degrees Celsius, does anyone know about what 20 degrees Celsius is? Second?
30, 35?
No. 68. It's about the temperature of this room right now. So noontime, hottest time of the year, of the day in Mars could be about room temperature. If it could be, is that warmer? Oh, okay. Again, this is using formulas we haven't had. That's what it's asking about, room temperature. Mars' coldest temperature is around negative 140 degrees Celsius. That would be about negative 220 Fahrenheit. Guess what? Not going to live in that, okay? Anywhere close to it. So that really wasn't that useful. Now, every now and then they will have some of these other blurbs, and this one's called a case study. Is it worth the cost to send up these probes to Mars to, yeah, okay, I see someone shaking his head. Many people would say, no, how many people could you feed? How many could you put in the medicine? I mean, what could you do with that other than that?
Human evolution.
What's that?
Human evolution.
Okay. Yeah, possibly that is a thing of it, but we have learned so much by going into space and finding things and studying, and we have much better ideas of probably how things came about. So, well, I'm sure there's still arguments both ways, but that's a nice little blurb to read. Now, again, these are using formulas we don't have. Because Mars is quite a bit smaller than Earth, its acceleration due to gravity is much less. So there's a question here, how fast would a rock falling from a 60-meter high cliff on Mars be traveling when it hit the Martian surface? They say about 21 meters per second. I thought they would show what it would be on Earth. That would be closer to I don't know if they say it here, but that would be many times faster on Earth because the acceleration due to gravity is much less. So I won't go into that. All right, enough of that. Let's move on to Jupiter. Now you talk about another fascinating planet, and it has a lot of superlatives about it. Okay, let's back off and go back to our distance. Here's Sun, here's Earth, Mercury, Venus, Mars, halfway again, further from Earth, okay, 1.5. Jupiter, way out there, 5 times the distance from Earth, Sun to Earth as it is Sun to Jupiter, okay, 5 astronomical units, okay, is way out there. Now, I'm going to introduce another theory they're going to talk about later. In between Mars and Jupiter, what do we have? The asteroid belt. Now, here's what many believe, that was supposed to be another planet. Okay? But the huge, huge gravitational force field of Jupiter kept it from forming, kept it broken up. So therefore we have a bunch of rock out there. No one knows that for sure, but by far the most massive of the planet. 318 times the Earth's mass. Okay? That's a lot bigger. We're more massive than any of these others in here. It's 318 times what our mass is. What is it made up of? The lightest gases existent. Okay, that tells you how big it is. Hydrogen and helium are the very highest, lowest density. So they're the lightest of our gases, and that's what it's mostly made up of. So it's huge to have that much mass made up of that light of material. Now, it does have an iron silicate core, which is interesting. Iron, the most prevalent metal in the solar system, and silicates, that would be what our surface materials are made of. Most of the rocks you see out there are silicates. Okay, we'll see that in a later chapter too. So its core is solid, though it may be so hot it's liquid, but it would be what would normally be solid materials. Okay, so it is an enormous, enormous, enormous planet. Okay, here's a picture of that. The iron silicate core. Now this core, this little core in the middle of Jupiter is still 10 to 15 times the Earth's mass. You could get 10 or 15 Earths in that core, just in the core. Okay, that's incredible. Okay, so there's more iron in Jupiter than there is on Earth by a long shot. Okay, but it's all in that core. Now they have outside of that what they call liquid metallic hydrogen, which almost makes no sense. Okay? Hydrogen's a gas. It's really hard to get that to be a liquid. Okay? You have to take it down to very, very, very low temperatures. But these are not low temperatures there, I don't think. I think there's so much pressure, it's forced the gas molecules into liquid form. Okay? I think it's because of the huge gravitational attraction forces that. Now, when it says metallic hydrogen, there's sort of a reason for that too, and I hope your books have a periodic table somewhere in them. They may not. I asked them to put them in it. I don't know if they did. But you see, these are metals over here. These are your non-metals there. And hydrogen's over here. It really, chemically, structurally, is more like a metal, but it's a gas. Any of our temperatures and pressures. But under the pressure of this Jupiter, it actually becomes more metallic. Now, notice how thick these things are. They say how much mass is in here, but they say this is 35,000 kilometers thick. That's huge. Let's see. I'm just going to get the, if I can quickly here, sorry. Okay. Earth's radius. 6,380 kilometers. That's our radius. This is 35,000 kilometers. Talk about big. Huge. Okay. Then we have liquid hydrogen, not liquid metallic hydrogen. That's here. Liquid? Okay. Now this could be getting cold by the time you're out here because you're way out there. But also pressure too. So there's liquid hydrogen. And then here's your atmosphere of hydrogen, helium, ammonium. I think they mentioned methane too. They just say ammonia here. And those are clouds. And I mean, that's a very active atmosphere too. Not like ours. Ours is nitrogen and oxygen. This is hydrogen, helium, ammonia, and maybe some methane. Okay? And that's about 500 kilometers thick. So it's a huge atmosphere too. That's why I said there's no solid surface on Jupiter. That's the closest, and I'm not even sure it's solid. It may be liquid in there. I don't know what it is in there. Okay. Now, here's a picture, and a pretty good picture of Jupiter. They sent many probes out there. And this is called the Great Red Spot. What that represents? Remember, this is an atmosphere, a very active, volatile atmosphere. It's storming like crazy, and this is one storm. It's a huge storm. I think you could fit several Earths inside that storm. Huge storm, and it's been going on for as long as we've seen Jupiter, as long as we've had. Telescope strong enough to look at Jupiter, we've seen that storm. Now, it seems actually to be diminishing a little bit. So maybe it is going away, but it's been there decades, if not centuries. Okay? One big continuous storm made up of something. And then you see bands of weather. You know, it's really a very active planet as far as its atmosphere. There, can't remember now, I think this spot here is one of the coldest spots on the planet, and that's one of the, I mean, that's why it's such a big storm. Enormous variation going on there. Okay. I thought there was a blow-up picture. Oh, okay, here's what. Okay, here we go. Dynamic atmosphere, that's what I've been trying to say. I didn't quite use the term right. Let's go back to the one we saw before. There's the Great Red Spot, a huge storm. And here's a little white thing here, which could be the opposite kind of a storm, perhaps. And that's what they're talking about here. Here's a blow-up picture of that. There's part of the Great Red Spot, and then that white storm there. It's another big storm, but it's seems to be doing the opposite thing because that one's red, this one's white. Okay? And yeah, here's where they mention methane. Dynamic atmosphere, hydrogen, helium, ammonia, methane, some water in the atmosphere of Jupiter. And then the Great Red Spot. Okay? And I think your book probably goes into that a little more detail. I'll let you read that. Your picture in the book, the way they colored it, looks like the Great Yellow Spot, but that's really red when you look at it. I don't know why they colored it this way. And you'll see a lot of what we've talked about with slightly different figures here. Now, the next thing we say here, a large system of varying satellites. What do we mean by that? Lots of different kinds of moons. Lots of different kinds of moons. Now, I don't know if your book says, but some book I've read numbered them at one time to be in the 50s, and they figured they hadn't gotten them all identified yet. I don't see it here, so it must have been somewhere else I was reading that. But it seems like I've seen 52 or more known moons. Okay? Now, I wish I could see that picture, but they don't show it in this text as well. Okay? Now, I'm sorry, I said it backwards. The Great Red Spot soars about 25 kilometers above the surrounding clouds, is the coldest place on the planet. But it says, in general, Jupiter's dark features are warmer and the light features are colder, and yet it says the Great Red Spot is the coldest spot on the planet. Well, what in the world is that one? That's another cold spot, but not as cold as the Great Red Spot. I don't know. So, here we go. Now, in your book, these are listed slightly, they're pictured slightly differently, but here they are. These are the largest, 4 of the largest moons of Jupiter, the 4 largest moons. They have a special name. They're named the Galilean moons. Now, does that have anything to do with the Sea of Galilee, you think? No, we're close. Why would they name them the Galilean moons?
Because Galileo discovered
Galileo was the one who discovered them. Now, what did Galileo do? Remember, you don't know. Some of you have been in the class before, the physical science 2 class. Galileo was, and many people consider him, and maybe Newton, to be the fathers of modern science. He was an incredible mind. He got himself into trouble with that mind sometimes because he accepted some scientific evidence that went against what everybody else believed, and they got really mad at it. Would have almost executed him, but he was such a famous scientist, they just put him under house arrest and forced him to recant his scientific thinking, but he privately wrote not to be published until after he died that he didn't mean to recant a bit of it. They just forced him to do so. But anyway, he had heard that someone had stacked together lenses in a certain way that they could magnify things greatly and see features of the moon, say. Well, he read about it, studied it, and he decided to build one for himself. But he was such a great guy, great mind. His was way superior to the others that had been invented. Way better. So he was able to look at the night sky, and he saw Jupiter. And he was amazed, because he could see those features were spinning. And that's hey. And they already knew that the sun spun. They knew Jupiter spun now. He said, why the Earth wouldn't be spinning? that may account for the stars and the sun appearing to move. They're not moving. They're stationary. We're spinning, and it makes them look like they move. Oh boy, did that upset people. Earth is fixed. We're the most important thing in the universe. We're there. Everything else goes around us. You know, just like a teenager, right? Never mind, I didn't say that. Okay? That the whole world revolves around. No. And he got in serious trouble for that. Well, with his new improved telescope, he could see Jupiter, see it spinning, but he also saw 4 bodies going around it. He said, hey, if these bodies can go around Jupiter, why can't we go around the sun? Because see, this other guy named Copernicus had already come up with that idea. And he had read Copernicus and said, you know, this guy makes sense. And as soon as he agreed with him, see, there was a big difference here. Copernicus lived over here in Poland, and Galileo lived in Italy. And where was the head of the church? Rome, the Vatican. He was just, you know, Pisa, not very far away. Copernicus was way up there. But you know what? Copernicus hadn't been completely open with his communications about this because he was actually a monk in the church. He could have really gotten in serious problems. So he only communicated with other scientists, didn't communicate this stuff to Rome. He didn't publish it outright, but Galileo read where he had been working on this, said, this makes sense. So because he discovered these 4 moons going around Jupiter, he said, hey, why can't we be going around the thing? It fits everything Copernicus has just said. See, Copernicus did it without the advantage of having his improved telescope. He saw things Copernicus couldn't see. Said, yes, this has to be true. And therefore was put in jail for the rest of his life in his own home. So here are the 4 Galilean moons. The 4 biggest moons of Jupiter. And this is pictured by NASA's Galileo spacecraft, which is pretty appropriate, while orbiting Jupiter. From left to right, no, this is from top to bottom, left to right, top to bottom. They are, make sure I got them right, Io, E-I-E-I-O, no, Europa, the smallest one, Ganymede, the largest one, and Callisto, okay? Io and Europa, the top 2, are about the size of the Earth's moon. Ganymede and Callisto are larger than Mercury, okay? Larger than the closest, one of the planets. And they are moons of another planet. That just shows how massive Jupiter is. Enormous. And it has tons more moons, not this big. And then Saturn has some big ones too. I think Titan is just below Ganymede and Callisto. They're very close in size. Now, all right. Example 5.9 is another one that's just sort of a made-up problem, getting you to look at it. Now let's see if this next slide is here. The next one you see in the text on page 389, we're going to see it later, but that's when we're going to be talking about comets. But keep in mind, Jupiter interacted with a comet, probably many times, but someone got to see, not exactly happening, but shortly after it happened. Okay. So now we're ready to move on. Okay. Now don't let me go. Whoa! Is it 3:15? 3:12. Close enough. I think we'll stop and start with Saturn next time. Okay? So we got a fair amount covered today. Okay. I'll use that to mark my space. But I want to get started on the lab. Do you need to take a little break before we do? Yay or nay? Okay. Let's try to keep it less than 5 minutes. We've got 3 minutes of class time before we get into lab time. So 3 minutes class time, 2 minutes lab time. We'll come back less than 5 if possible, folks. Okay. And before you go, let me go on and pass out the lab to you, or else I'll just pass out. I don't know. Some people were here last time and got copies of it. Some had left already. Who didn't get a copy? You got a copy? Did you get a copy? Did you get a copy? You got one, did you? You got one?
Which lab we are going?
What's that?
Which lab we are going? 252?
No, we're going to be here. May not have enough for everybody, everybody who's here today, but a few people have added since I had these run off, so we may be a little short. Okay, I'm going to put this on hold. Okay, so all that I've said so far, which wasn't much, I admit, that wasn't recorded. So people not here, sorry about that. You missed a little bit. We talked about what the definition of meridian and transit. You'll read the lab and see it, and what the ecliptic is. Okay, really feel bad for Bertram because I gave him the lab so he could follow it, but we haven't started writing anything yet. Okay, there's the Earth. Okay, and here we are standing in Bessemer, Alabama. Okay, there we are. Should have a coat on because it's winter time here. All right, now we're at okay. Here is our celestial equator, about there. I mean, not celestial. This is the equator, right there. We're about, and I could go get the book for you, but I'll tell you, we're at 33 degrees, 23 minutes, 45 seconds north of the equator. That's our latitude, okay? That's our latitude. That's where we are on the surface of the Earth, okay? Bessemer, Alabama, okay? Here's the equator, and if you go up from here, okay, there's 15 degrees, I'm pretty sure this is, 15 degrees, and there's 30 degrees. That puts us right around New Orleans, okay, or a little further over Mobile, okay? Then you go up another 3 degrees, and that gets us up to Birmingham, our Bessemer. Okay, 33 degrees, 23 minutes, and 45 seconds. Okay, that's how many degrees we are north of the equator. Okay, now let's draw our celestial sphere. Okay, this is our horizon. Okay, and here's the celestial sphere. My best. I can't draw semicircles very well, but that's the best I can do. Directly, and by the way, that's our meridian there. Okay, we talked about that. Okay, from due north to due south. So our north pole is somewhere up this way, about 60 degrees there. So guess what? There is Polaris, the North Star. Little bitty star, but there it is on the celestial sphere. This point directly overhead is called our zenith, okay? Now, that's where we're standing. So the celestial equator would be 33 degrees, 23 minutes, and 45 seconds from our zenith, because that's directly overhead us. This is the celestial equator. Sort of get a feel for it here? Okay. And then this is 90 degrees from that. There's the North Star. Okay? That should be 90 degrees. I don't know if it is or not, but you can imagine it is. I don't draw well. Okay. Now, what it's asking you to prove is the angle theta, alpha, that's alpha, the observer's latitude, so that's what I've said. I've said this is alpha. So you don't have to write 32 degrees, 23 minutes, 45 seconds. Just call it alpha. Call alpha. No, okay, never mind. Okay, and that our observer's latitude, that's our latitude, is in fact the same as the angle alpha of the celestial pole over the northern horizon. That's what we're there to prove. How can you prove that? Like I just said, this is alpha, our latitude. So this would be alpha, the angle between the celestial equator and our zenith, right? So we'll call that alpha 2. This is alpha here, okay? Now, why would this be alpha? Or is it? Are they asking us to prove something that can't be true? Okay? Hint. What did I just say? This is 90 degrees here, isn't it? All right? So, this is alpha. This bigger angle here would be 90 minus alpha, right? But this angle here, between our zenith and the northern horizon, this has to be 90, doesn't it? But this angle here is that same 90 minus alpha, so guess what? That's got to be alpha. Because if this is 90 minus alpha, this has to be alpha. Does everybody see that? Kinda, a little bit, maybe. Vague? Or is it clear? It's got to be. Now, you need to write down whatever it takes for you to know that that's true, and for you to communicate to me, you know that that's true. So whatever it takes to demonstrate that right here on this illustration. If you're doing the same things I did, you may already have it done. Did you? Okay. Because that's going to get a grade, okay? You're going to have something there that convinces me you understand this has got to be the same as this. Basically, I think we just did it. Any questions on that? You need me to explain or go over anything else? You got it? Okay, what? Which piece? Okay, this was given. This is called alpha. That's our latitude, how far we are above the equator. Okay? And because of that, that's how far it is above the celestial equator to our zenith, up there on the celestial sphere. You see why that has to be true? Celestial equator is right above the real equator. This is the equator here. Our zenith is right above us, so that angle also has to be this angle alpha. Right? Now, because the celestial equator, and every equator, is exactly 90 degrees from the North Pole, North Star. North Star is there, and on the globe. The equator is here, 90 degrees from that is the North Pole. 90 degrees south of it is the South Pole. That's exactly where the North Pole is. So therefore, the celestial North Pole has to be 90 degrees from the celestial equator. It's halfway to 180. See, the North Pole, South Pole, halfway between that is the equator. Equal size north and south. So this has to be 90 degrees here between the celestial equator and the celestial North Pole, pole star. Okay? Now, this portion of that is alpha. We just said that. Because it's alpha here, it's alpha there. Well, this is the difference between 90 degrees and alpha. Okay? We could actually subtract it and see what it is. 56 degrees, blah, 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 blah. So, yeah. That's what this would have to be. But then it's pretty obvious, isn't it, that this is 90 degrees. And if this is the difference between 90 and alpha, and this is 90, then this has to be alpha. right?
And then it's also the same on the other side as well.
Yeah, this would be 90 minus alpha here too. Yes, and then this would be alpha. Exactly. Okay? Can you fill that in well enough for me to understand you understand what we're saying? Okay? Give it your best shot. Okay. Okay. When everybody has that picture filled in enough to convince me, which I don't take a lot of convincing, I have to see something there, and it needs to be correct. Okay. You finish with that, let me know, and we'll move to 2. Poor Bertram. I just realized I was doing all this pointing here. That doesn't get projected. Okay. I should have been pointing with my pen here. Because this is alpha, that has to be alpha, this has to be 90 degrees, and this is the difference between 90 and alpha. Oops. Okay. But this also is 90 degrees there. And if this is the difference between 90 and alpha, that leaves this having to be alpha. Okay. Maybe that can help y'all a little too. But not just Bertram, anyone who's not here, but Bertram can't be here because of his work schedule. Okay, y'all got it? Okay. Is that a yes for everybody? Okay, still working. Okay. And I hope your picture's better than mine. Okay. I don't want anything messy like this. No, I'm just kidding. Okay. And I'll say this while y'all are working on this. This is probably the longest lab we're going to have all term. Okay. I don't know why in my other class, the first lab is by far the longest and most detailed and complicated lab of all term. You know, I don't know why they launch out this way. The rest of them will be, you know, okay too. But no, actually the third lab, because you got to do some of that at home, it's going to take you 2 weeks. But I'm not talking about that length. In class time, the longest probably of them all. Okay. Everybody's still working. Got it? Everybody? Okay. So if you turn one page, okay, top of page 361, it says, if the celestial pole is an angle alpha above the northern horizon, that's what we just said, we can then establish the location of the celestial equator. It's 90 degrees from that, and that's where we went, okay? So that the angle along the meridian, okay, that circle up there is the meridian, the semicircle, makes over the southern hemisphere. That is from southern horizon up to celestial equator. Guess what that's going to be? If this is alpha, this is 90 minus alpha. Okay, here's a question, folks. So the celestial equator starts in the east, climbs to an angle of 90 minus alpha over the southern horizon, and then drops down to the west of that horizon. Boy, that's a strange sentence. If the celestial pole, right here, makes an angle of 40 degrees above the northern horizon, what will be the angle between the southern horizon and the equator? If this is 40, what is this going to be? 50. Y'all are good. Y'all are good. Okay? Now, here's question 3. What if we move to Quito, Ecuador? Now, when you see that term, that country Ecuador, I don't want you to just think of migrants or things, you know, a few may have come from there. What does that word look like almost? It does. It looks just like equator. I wonder why they got that name. It's sitting right on the equator. That's in South America, if I could get to the right continent here. There we are. And there's Ecuador, sitting right across the equator. That's why they named it that. It's Spanish for equator, I guess. And Quito, which is the capital, guess where it sits? Smack dab on the equator, just about. I mean, you can't get much closer. Okay? So if you're at Quito, Ecuador,
You'd be
okay?
very hot.
Second?
You'd be very hot and sweaty.
Okay, that's what I used to think too, until I found out Quito, because it's inland a ways. See, here's the coast, that would be hot and sweaty. But it's inland a ways, and when you go inland, we go hot. And it's actually a wonderful climate. Almost perfect. The altitude gives it just enough coolness, you get the range, you get everything. It's just a delightful place from what I hear. I've never been there. Oh, I'm so jealous.
You want to change our field trip to there?
Oh yeah, let's do a field trip to Ecuador, to Quito. I'm so jealous. I have a niece, my older brother's younger girl, did her graduate work in climatology and stuff. A lot of the same stuff we'll be doing, way beyond what I am. But she went to London several times to do research using data that they had, because, you know, Britain, the Queen of the Oceans, they had lots of data for long periods of time on climate and stuff. But she went to this other little place, just writes me like crazy. She got to go to the Galapagos Islands. Anyone know what they are? They're far enough from anything that it's almost a completely different world. The types of animals and species and stuff that have developed there were not mixed with any others. Birds didn't fly that, well, maybe a few birds did, but, you know, basically, so you have all these things. Have y'all heard of a duck-billed platypus? It's a really strange animal that we have here. They have things that are even more. They have sea turtles that are the size of pigs. You know, I mean, they're huge. Their whole, you know, their predators and stuff are very different. So species didn't have to. I mean, just a fascinating place to go. Now, but this doesn't turn anyone off. But a couple of pretty famous scientists, Leakey and the evolution guy, Darwin. They both went and studied great detail things in Galapagos Islands, because it's just a world apart. She got to go there and study their meteorological data, because so many scientists have been there and reported so much stuff. I'd love to go to Galapagos just to see the varying fauna and, what's the other word? Mostly fauna, the animal life that's there. Okay, so we're there at Quito, Ecuador on our field trip, okay? Where is your celestial equator then?
0.
Okay, so now think about it. The celestial equator would be the projection of the equator from where you are. So if you're right on the equator, where is it?
Straight up.
Straight overhead, okay? I'm facing north, facing north, but the North Star is right on the horizon, because you can't get any more. That hole in the south is right down there, you know. And the celestial equator is directly overhead, east to west, directly overhead, because there we are. It's just like this, projected straight overhead. North facing north, south facing south, the celestial equator directly overhead, east to west. Okay. So there's number 3. Does that make sense? Okay. Now, we're not at Quito, Ecuador. We're somewhere else. Okay? But let's just be out there in space, and we're on the globe there. Okay? And let's just imagine that we did have that little light that I talked about last time in the center of the globe there, and it was projecting outward. And if the globe was just like this, then on our celestial sphere, there is the celestial equator going like this, okay? North Star is right like this, South Pole somewhere down in there, way below our horizon. And there we are. That's the picture it's shown here. Okay? Do the sun again. Okay. So here it is. Well, my ecliptic is the plane between him and me, the Earth. Okay? And you see that's not always, it's not the same as the celestial equator. Because it's tilted like this, and you're like that, and I'm going around you like this. Now, at some point, it's directly overhead. At some point, it's above you. At some point, it's overhead again. At some point, it's below you. Okay? So the equator moves according to the ecliptic. The ecliptic is the plane that cuts straight through like this. Okay? And that's what this figure is showing. Okay? I'll try to do it here. Okay? That tilt, by the way, is, you see it on here? How much? How many degrees? You see it on here?
23.5.
23.5 degrees, exactly. And in fact, if you were to look at this, of course, it has to have it backwards, okay? From 90 degrees, subtract 23.5, and you're at 66.5. And that's exactly where you find it, right here. That is a 66.5 degrees off from doing straight up. Hang on to that one. We're going to use it over and over and over and over again. 23.5 degrees is the amount the ecliptic is from the straight up. Okay? Now, so that's what we have there. Now, I'm going to try to do this with this as much as I can. All right. Let's say that we're at around the 21st of September, right here. The sun is just about directly over the equator here. That's called and as the Earth spins, half the time is daylight, half dark. Up here, half time daylight, half time dark. Down here, half time daylight, because we're right there. It's on the ecliptic. So that's called the autumn or autumnal. 12 hours daylight, 12 hours darkness. That's called equal night. What's the German word for night? Anyone know? Not. Equinox. That's what the 21st of September is really close to what we call autumnal equinox. Okay? Now you move on from there, and now we're getting close to, we've already passed it now, but we're at 90 degrees from there. And now the equator is way up here, the ecliptic is down here, and up in the northern hemisphere, we're tilted as far away from the sun as we ever are. That's around the 21st of December. You want to know what that is? Okay. 21st of December. Someone give me some characteristics of that.
4 days before Christmas.
Second?
4 days before Christmas.
Okay, yeah, Santa Claus is not coming. No. Got to be naughty, nice, not naughty. No. Okay. What that's called, second?
The winter solstice.
The winter solstice, perfectly. Okay? Now, where does that word solstice come from? S-O-M-L means? Sun. Solar, sun. Okay? And stis is the same root as our word still. Okay? What's happening there? Now, this is back in the old days when people didn't understand what was happening. Okay? They watched the sun. Remember, the sun crossed the meridian, your local meridian, and transit across that highest point of the day every day. And from basically July, August, September, November, December, it kept getting lower in the sky. And across that at noon every day, it was lower and lower and lower. And the ancients used to fear that 1 year or some time it may just keep falling and then get below the horizon and freeze to death. You'd never see the sun again. But they noticed as it went down, it slowed and it slowed down, day to day to day. And finally it stopped. It stood still. Winter solstice. It quit going down. And then after that, it started going up again when we moved on that way. Okay? Now, when we got back there about where you're sitting, we were now very close to where the sun crossed the equator again. Oh. Let's go back to the winter. Okay, like this. How far below the celestial equator was the ecliptic then? Well, do you remember this number? 23.5 degrees, because that's what the tilt is. 90 degrees? Yeah, 23.5 degrees. That's how far it was in the winter solstice, below the celestial equator. And then, on around March 21st, which will be coming up in a month, just a couple of months now, okay, we will be back on, right there on the equator again. So then we'll be, what will that be called? 12 hours darkness, 12 hours light. The what?
Is it daylight saving?
Okay, we usually do it sometime around there, but what is called is equal night again, equinox. Only that will be called the spring, or the other term for it is vernal equinox. Okay? Spring equinox. Equal day, equal night. And then when it rolls around to June the 21st, or something like that, where's the sun? Way above the celestial equator. How far way above? 23.5 degrees above, exactly. That's when the sun is the highest in the sky it will ever be. And that's called the summer solstice, because the sun climbs every day. Every day it climbs. And then on the 21st of June it quits climbing. It stands still, solstice, that is still. And after that it starts dropping again. Okay? So that's what this figure is illustrating. When this is the celestial equator, the one that's tilted because the thing is tilted at 23.5 degrees. The summer solstice, the sun's, the ecliptic is this that's flat, because that's where the sun is. We're in the plane of the sun. And at summer solstice, the sun is 23.5 degrees above the celestial equator. Winter solstice is 23.5 degrees below the celestial equator. The vernal equinox in the spring is when the ecliptic crosses the celestial equator. That's where the sun is directly overhead, everywhere on the planet at noon. It's not directly overhead, but it's 12 hours of daylight, 12 hours of darkness. Because right now it's getting dark, and what is it, 3:45? Woo, it's almost 4. You didn't stop me, did you? Okay, let me call roll again while I'm thinking of it. I'll have to get it twice. Zaria is still here. Good. Rod is still here. Good. Gavin is still here. Good. Bertram, he just came in earlier. Samaya is still here. I thought so. On the other side of the globe there. Okay. Corey is still here. Thomas Earl is still here. Seth is still here. Yeah, in the corner. Okay. Brandis, Janelle Lang, we haven't seen from the beginning. And Rashad didn't come in yet today, did he? Okay. Michael is still here. Wait. No, Michaela is still here. Sorry. I have a Michaela and a Michael now. So Michaela is still here. Cole didn't make it in today, right? Patel is still here. Reggie is still here. Diego is still here. Michael is still here. No, he isn't. Did we lose him?
Yeah.
Whoops. Gracious. Okay. And Radeja is still here. Oh, and Melanie's still here. Forget. Derek never made it in, did he? And Marcus never made it in. Okay. Cole didn't make it in. Okay, I think I've accounted for everybody there. Okay, who am I? Oh yeah, Bertram. All right, good deal. Sorry, had to do a break there. Okay, I did a break. Oh, so watch out. I'll lose my train of thought. I'll lose everything. Okay, so you get the idea of why we have the season set. What I was going to say, at 4 o'clock in the afternoon, look how dark it's getting. Okay? Not as dark as it was last week at 4 o'clock, or the week before at 4 o'clock, or December 21st at 4 o'clock, it was even darker than this. Okay? But next week at 4 o'clock, a little bit lighter until we get to March, and then it'll be still a couple hours before it gets dark. Okay? But then in the summertime, 21st of June, it's not going to be like as bright as noon, but it's going to be much brighter than this. Okay? So yeah, it changes. Now I did have, when I was teaching this class one time, this has been several years ago now, had a student who was originally from Kenya. And she said that was the hardest thing for her to get used to, that the days changed in length. Because Kenya, like Ecuador, sits right across the equator. And all of her days, all year long, were 12 and 12, 12 and 12, 12 and 12. But not here. Okay. Days get shorter in the winter, longer in the summer. Okay. Daylight. Days are still 24 hours. All right, so that's what that figure is showing. All right. Now, and this is what this one shows too. I think these are summer solstice and winter solstice. Okay. Our ecliptic, remember, is about 33.5 degrees, 56.5 degrees above the horizon, southern horizon. That's the celestial equator. I'm sorry, celestial equator is there. In the summertime, the sun is up here. It rises earlier in the morning, goes higher in the sky, and sets later in the day. In the wintertime, it's down here. It rises south of east, goes up to a lower elevation at noon, and then sets south of west for shorter days. That's what these figures are showing. Higher in the summer solstice, lowest in the winter solstice. Okay? Now, what they're showing here, and this is a slightly different term than the one we used before. Okay? It is a very different term. Okay? Before we talked about altitude of an object over the horizon. Now we're going to talk about altitude of an object over the celestial equator. So if that's our object, and this is our celestial equator, the angle between the celestial equator and that object, that is another, and we call that declination. Declination. From the Earth's equator up to the point where that object is in the sky. Okay? Declination. Now, guess what? That never varies. Okay? Because this is the Earth here, and let's say that the object is here, or it's that far above the equator. When we go over here, it's still that far above the equator. It hasn't changed. We're just moving around the sun. Okay? So the declination of an object does not change. Okay? Now, there's another measure, and that's called right ascension. Now, before we talked about azimuth angle, which was from due south up to where the object is. Now we're going to be talking about someplace along the celestial equator And that's what we're going to measure from. And celestial equators are sort of hard to deal with, aren't they? Because they're somewhere out there on the sphere. But there is one place, there are two places that are very fixed. The vernal equinox, where the ecliptic crosses the celestial equator, and that's the vernal, and the autumnal equinox, where they cross. Those are fixed. We're going to use the vernal equinox, which is always considered to be around the 21st of March. So with those two, the angle from there going around the celestial equator until you get right under that object, that's going to be called right ascension. And the one from the celestial equator up to that object, that's going to be called your declination. So those two measures, it's just like latitude, longitude. Latitude would be right ascension. This is the object on the celestial equator. And longitude, that's from the prime meridian over here in London, England, near London, I don't know, Greenwich, England, how far you are. That's right ascension. Okay? So, before we get into that, here's a problem, folks. Particular aspect of right ascension coordinate. Okay? What do we measure it by? Well, I was acting like we measured it in degrees. And in some senses we sort of do, except we actually measure it in hours. How long after crossing something would you cross that mark? Okay? And we subdivide it in minutes and seconds of time rather than minutes and seconds of degrees. So that gets sort of confusing. They're almost measuring the same type of thing, but using some of the same words, whereas angles measure in degrees, but a fraction of that would be a minute and a second. Whereas time measures in hours, a fraction of that in minutes and seconds. So boy, we got a problem here. So let's see if we can make a connection here. How long does it take for an object out there in space, okay, remember, we're spinning, how many degrees is it from the time it's, say, here until it's there again? How many degrees is the Earth spun one time around? 360 degrees. Okay. Let me back up. That's true. Okay. But it's not the spin of the Earth, it's the revolution of the Earth around the sun. How long does it take to do that? 365 days. But that's 360 degrees. So it's almost a degree a day, isn't it? Okay, very close to a degree a day. We're going to approximate it that way. Okay? So that's what we're doing here. Now we're on page 363 here. Okay? 363 all the way around the celestial equator is 24 hours. So we treat it the same way. Just like it takes 24 hours for us to spin one, it's going to be 360 degrees. Okay? So hours, degrees. There is the tie-in. Okay? So we know this ratio is true. Now I'm going to erase this and regret I did it, but we're going to need it again, but I need the space now. Okay. So we know that 360 degrees of spin, okay, that would be an angle thing. Second? One complete rotation. And how many hours that takes to do is 24 hours. So there is those are equivalent things. One in degree, one in hours. Okay? So the question is, how many degrees of arc, so this is arc, and this is what you might call time, right ascension. Yeah, let's call that right ascension. 24 hours of right ascension is equivalent to 360 degrees of arc. Okay? The question here, in number 4 on the bottom of page 363, how many degrees of arc, so this is how many degrees of arc are equivalent to, where is it, 1 hour of right ascension. That is a proportion. Say again? 15, right on the nose. Divide this by 24, divide that by 24, and you get 15 degrees of arc are equivalent to 1 hour of right ascension. Perfect. Perfect. Okay? Now, here's where things get a little, they're not really confusing, but you're using the same term for different things. How many minutes of right ascension are equivalent to 1 degree of arc? So you want to get, you got 15 degrees of arc. Okay, wait, we'll see. 1 hour, we know that, of right ascension. Okay, but the question is, how many minutes of arc, minutes of right ascension are equivalent to 1 degree of arc. So you set up your proportion that way. Wait, you can't quite do that because this is minutes, that's hours. How many minutes in an hour?
60.
60, I can't get it to erase. So change that 1 hour to 60 minutes. 60 minutes of right ascension. Now we can do the ratio. And what would that come out being? Not quite. Now look at this. What do you multiply this by to get 60? You'd have to multiply that by to get, the ratio is the same. 4. Exactly. So that would be 4 minutes of right ascension. Okay? 4 minutes of right ascension.
Can you elaborate a little more so I can understand?
What's that?
Can you elaborate a little more so I can understand?
Okay. What did you, okay, this is a proportion. These things are the same. 1 is to 15 as what is to 60. You could do cross multiplying if you wanted to. 15x, if you wanted to do that, is equal to 60 divided by 15 and you get 4. That's one way to do it. So just notice that this number is 4 times that, so this number has to be 4 times that. Right? 60 is 4 times 15. 4 minutes would be 4 times 1 degree. I mean, you don't really multiply degrees, you have to get there. But that would be 4 minutes of right ascension. To get that proportion to work out. Just like here, that was 15 times there, so it's 15 up there. This is 4, the denominator is 4 times the numerator, so it'll be 4 times the numerator. The units are just different. Degrees are minutes, degrees are minutes. Degrees are minutes by ascension. Okay. The next question, though, is how many minutes of arc are equivalent to 1 minute of right ascension? Okay? We know from this that 1 degree of arc is equivalent to 4 minutes of right ascension. And then the question is, how many minutes of arc are equivalent to 1 minute of right ascension? Isn't that what it asks for? Yeah. Well, this is in degrees. How many minutes are in a degree? Say again? How many minutes are in a degree? Where do you get a point? How many minutes are in a degree? Okay? If you had a protractor here, and that was 1 degree, how many minutes are in that degree? Second? 1. How many minutes are in an hour?
60.
60. And 60 minutes in a degree. 60 seconds in a minute. Degrees and hours, even though they're measuring different things, they have the same breakdown. 60 minutes in a degree, 60 seconds in a minute, whether you're talking about time or arc, okay? No matter which. So this would be the same as 60 minutes of arc. That's 1 degree of arc, okay? So what would this question mark be? 15 again, because 4 will go into 60 15 times, 1 will go into 15 15 times. So that would be 15 minutes of right ascension. No, of arc. Of arc is equivalent to 1 minute of right ascension. Now that's what gets a little bizarre. You're talking about minutes, but that's minutes of arc as opposed to minutes of right ascension.
What was 5?
4 minutes.
4.
Okay? Because 15 times 4 is 60, 15 times
So,
1 is 15.
1 60 minutes and 60 degrees, like what was that?
Say that again.
1 degree, so 60 minutes.
Okay, when you break something into minutes, no matter what you're breaking, there's 60 of them in there. If you're breaking a degree into minutes, there's 60 minutes in a degree. If you're breaking an hour into minutes, there's 60 minutes in an hour. Anything, and that's from the Sumerians, the old ancient Babylonians. They came up with this 60 thing, and everybody else has used it ever since. Okay? Don't know why. Maybe they had 6 fingers on a hand. I don't know. No, I'm just kidding. Okay. That's not it. Okay. So that's part B. Now the fun part. Okay? We're going to locate some stars. Okay? Now I'm going to do the first one for you, and I want you to watch and listen to what I say, and then I'll let you do it. Yuck, I won't. Okay. Why does the string know to do this right when I'm ready to use it? Been hanging in there for months, and then when I go to use it, it unties itself. I don't know how it did that. Wait a minute. I have fumbly fingers, so it takes me a long time to tie a knot. Get it to untie first. Okay, there we go. I may be old, but I'm slow. Okay. Can't get this to work. Okay. One time around there. Up there. Come around. Okay, now I got it. Okay. Okay. This, you read this sort of upside down, but yeah, we'll manage. Okay. The question number 8 says, now this is talking about if you have a celestial globe. We don't. We have a star chart, but we use a lot of the same concepts in it. So that's what we're going to use. The trouble is the celestial globe would be a 360 degrees in every dimension. This one, we're limited. So we are going to have some that we can't get answers to. But where we'll begin, now remind me where right ascension is measured from. Anyone remember that? I know it was a long time ago, like 15, 20 minutes. Where do we measure right ascension from?
From the
vernal equinox. And what's true about the vernal equinox? What crosses then?
celestial equation.
Second?
Celestial equation.
A little up.
Celestial equation.
The celestial equator crosses what?
Vernal equinox.
The ecliptic. at the vernal equinox. So I know this is going to be hard to see from back there where you're sitting, but I want you to notice this. This circle here is our equator, and it says it right there, equator. That is the celestial equator right there. It's a solid circle that goes this way. Now, you'll also see a dotted circle that goes this way. That is the ecliptic. Okay? So, what we do, we turn, now what you wind up doing is holding this string. This string up here is on the North Pole, right there, North Pole, okay? And you line it up with this circle down here. That's where you're standing, okay? And then you turn this around to the vernal equinox, which is about what day?
21st December.
Of what?
21st December.
Of what month you said?
December.
December would be the winter solstice. When is
March.
the vernal or spring equinox?
March.
March the 21st, okay? Turn this around to March 21st, and look there what happens. Okay? There you see the dotted line here, the ecliptic, and there it says ecliptic, crosses the equator right there on the 21st of, right at the 21st of March. There's March, and it goes from 1 to 31, so that's 21st of March. Okay? Where they cross there. Okay? Now, what you do, you first determine right ascension. Now, right ascension, we're going to measure in hours now, so we're going to use the hour scale here. See, this is days here, but we're going to use the hour scale, and you'll see this is at noon, the way it's set up right now, and the hours count over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That would be midnight. 1, 2, 3, 4. Yeah, so you have 24 hours around. That's also right ascension. Okay? So 6 hours and 43 minutes, right ascension. Okay? 6 hours. 1, 2, 3, 4, 5, 6. And then 43 minutes would be about 2/3 of the way there. Because 3/4 of the way there. Because 45 minutes would be 3/4. So somewhere about there. Okay? Now what I'm going to do is pick off a day that represents. And that looks about like the 1st of July. I'm using that as a surrogate here. So I'm going to turn the 1st of July down here. Okay? Until it's at the bottom. 1st of July. See, I'm doing my right ascension now. 1st of July, if I could get it to turn. Okay. Right there. Okay. There we have there we go. Okay. Now, that's our right ascension. We're lined up along it. Now we do declination. What's declination measured from? Anyone remember that?
From object to right ascension. From us to right ascension.
Okay, that's right ascension. What is declination measured from? Anybody? Declination. Oh, it's on this thing, isn't it? Declination is measured from you see that solid circle on page 363, top of the page?
Yeah.
The declination is going upward there from the celestial equator to the object. So that's what you're doing, celestial equator. Okay, but if it's a minus 16.39, 16 degrees 39 minutes, where is that? South of the celestial equator. Well, the celestial equator is this circle right there. We see it, equator, right? And we're going south about 16 degrees. Now, that's hard to pick out here. But there is a very bright star right there at the edge there. And what is that star's name? Sirius. In fact, it's the brightest star in the sky. Not Sirius. S-I-R-I-U-S. Sirius. Okay? Are you serious? Yeah, no. That's serious. Okay. All right. Someone want to try the next one? Don't be shy. I'll help you. I'll walk you through it. Somebody, volunteer. Time's a wasting, folks.
I'll do it.
Okay. All right. And then Melanie will do the next one. Okay. Now, where are we? What is it? Where do we start? Right ascension. Where is right ascension measured from? Where the vertical, where the ecliptic crosses the celestial equator. But it crosses twice a year, so which one do we use?
March.
March 21st. You turn March 21st, so it's down here at the bottom. Okay?
That's so cool.
Yeah. Okay? And then you'll see right there, look at that. This is the ecliptic, the dotted line. There's the equator. They cross right there. Okay, so put your string there. But you don't have to, you don't. Okay? And we move right ascension, coming this way, 6 hours and 22 minutes. Now don't move anything, just count. There's 1 hour, 2 hours, okay?
Wait.
Yeah, just count on your finger. I mean, go 1, 2, 3, 4, 5, 6. And then 22 minutes would be about a third of the way, right? So move your string around till it's between, about a third of the way between 6 and 5. Right about, oh, that looks good. Now pick a date right there.
Pick a date.
Yeah.
June 25th.
June 25th. Now turn June 25th till it's down there. Okay, you're doing the right ascension now. She's been living right close that far. I'll tell you in a minute. Okay, you're on it? Okay. Okay, now June 25th. Right there, yeah, perfect, perfect. But where are we on declination?
22 minutes.
No.
No, 52.
Minus 52, that's south of the equator. Guess what? You can't see 52 south. So all you can answer is something south of, Lord, what do we call that? Let's call it something south of Lepus. L-E-P-U-S. L-E-P-U-S is a constellation. It's not a star. It's something south of that. Okay? Now, who wants to go next? Was it Melanie? Okay? So the star name was something south of Lepus. We can't see it. We can't see that star here. All right. Where do you begin? Where is right ascension measured from?
Celestial.
Okay? The
Celestial equator.
where the celestial equator crosses the
One.
okay, now, it's at the vernal equinox, which is when the celestial equator crosses the ecliptic. Exactly. So you turn it to okay, turn it down. Yeah, this is down there. Okay, and start at March 21st. That's the vernal equinox.
You turn the
March 21st. You want it to be on this little tag right there. See right there, that little
okay.
March
Sorry.
21st. And y'all can get up and move around. A couple of people are, but you can do it too. March 21st. Okay, 21st. Oh, yeah, you're right. Okay, I'm sorry. I was looking at the wrong one. Okay, March 21st. And then declination or right ascension is how much?
38 plus 38.
A little more than 18 and a half hours. You got some counting to do here. Okay, from here, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 and a half. So move the string to your halfway in between the 6 and where the 5 would be there. Right there. Oh, yeah, hold tight so you can see better. Right there. Yeah. And halfway. Too far. Yeah. Something like that. Pick a date under there.
December 25th.
Okay, December 24th, 23rd. Move that down here. December 23rd, move it down there. This is getting our right ascension. This 23rd? Or the 27th?
Oh, okay, my bad.
Okay.
It's okay.
Yeah, that looks good. Now, what is your declination? And what does declination mean?
38
North of the
degrees,
equator.
2 seconds.
Now, here is the equator here. Celestial equator is that circle there. This is the North Pole, so that would be 90. So we're 38 degrees north of the equator. So that's a little over a third of the way. So, yeah. Okay, but if you hold the string over the circle down there, see you're tilted. What are you awfully close to? Ah, there it is, Vega, V-E-G-A, Vega, that's that bright star, Vega. Now here's the surprising thing, if I'm not mistaken, I believe I'm right on this, at some point long time ago, Vega was our North Star, okay, because we are precessing. We haven't talked about this yet, but we're precessing, and we sometimes don't point. But it takes thousands of years for that to happen, so the North Star will always be clear. All right, so you got number 3 was Vega. Number 4, where do we begin?
Right ascension.
Okay, right ascension. And where do we begin the right ascension?
The ecliptic and the celestial equation.
Okay, the celestial equator crosses the ecliptic, but it crosses it twice a year. Which one do we use?
Mars.
Vernal or spring. Okay, so you start there. March 21st. March 21st. Okay. And you'll notice there, looky there, there's the eclipse, the dotted line, there's the equator, so they cross right there. Clean. Got it.
Great. So what you call it?
Okay. Now you count over from there, 5 hours and 12 minutes, so about 5 1/4 hours. Starting here, make your hours. 1, 2, 3 and 1/4. Move the string around there. That's all right. Pick a date under there. Okay, June 10th. Turn June 10th back around there. Okay, you're on June 10th. Good. All right. And then you go -8 degrees and 15 seconds. Okay. Now, if this is 90 degrees, you're somewhere 40 to 50 degrees north, so this would be 40 south. So 50, oh, there's a bright star there. What is that? Right under. Rigel or Regal. R-I-G-E-L. Rigel or Regal, Rigel, Rigel, something like that. R-I-G-E-L. That's number 4 there.
So how do you measure the 8?
What's that?
How do you measure magnitude 8?
The -8, you just estimate it. Okay? Because you know that this is 90 degrees between the celestial equator and there, and you're south, so just make it guess. Okay. All right. Next, okay, you're going to do the next one. This is right ascension, 7 hours. Where do you begin the right ascension?
March 21st.
March 21st. Line that up at the bottom, March 21st. R-I-G-E-L, right. March 21st, and you notice right there, the equator crosses the ecliptic right there. The equator is a solid circle, ecliptic is a dead circle. So, okay, you're counting how many hours?
7.
Okay, about 7.5 hours, a little more than that maybe. So here's 1 hour. So count 2, 3, 4, 5, 6, 7, and then about a little over half an hour more. Move your string. Don't go 4 hours. Half hour past 5. Between 4 and 5 and 5 and 4. Check a date into there.
16.
Okay, 16, that sounds good. I'll turn to July 16th down there. Okay, you're right on it. And now you're plus 5 degrees, 21 minutes. Yeah. A little bit north of the celestial equator. See, that's 90 degrees, just north of it. You see a big star there? Procyon. 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 Now, if you remember from our star chart, the Hertzsprung-Russell star chart thing that we did, that was one that was a Procyon A and a Procyon B. It was a binary star. The Procyon B was a white dwarf, but the Procyon A was a big normal secret star. All right, who's next? Okay. Oh, you've already done it. Okay. Okay, I should have figured he would figure this out, huh? Okay. Where do you begin?
March 21st.
Got it.
2019.
Right in the meeting, which is that dotted line circle, crosses the equator, yeah, you're right there. And then you count how much from the 14 hours and 36 minutes, so it's about 14 and a half hours. Or counting up, yeah, 1. So bring your thing around up between 10 and 9. Little foot, fairly close to 9. Yeah, there's a date. October 26th. So right around there. So I already figured this out. Which is way off scale. See, you're going to have anything. Okay. All right. It's something south of, way south of, down here, let's say it's south of Libra. Something south of Libra. Libra, that's a constellation. Maybe it's a star way south of in that, I don't know. It's off scale, we can't tell. Let's see.
Okay, I'm sorry.
Let's see. Just for funsies here, were you on the thing there? I hadn't tried this before. You said yours was October 26th?
Yes.
Okay, yeah, you're right on that. If we flip over, hey! Okay. I didn't realize this. If we flipped over, we'd see it, but we're still below it, but you can see the name of that star. It is one of the brightest ones. It's Arcturus. So you don't have to say something south of Libra. Say Arcturus. 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 Arcturus.
Okay.
Arcturus. So let's go to that other one that was something south of. Was that yours?
It was the second one.
Yeah, the second one. And that was
Something south of
yeah, 6 hours and 22 minutes from that. Let's do it quickly here if I can. I don't do anything very quickly. Turn the wrong way with one problem. March 21st. Right there. And 6 hours and 22 minutes. You want to do it?
Sure.
Okay. I got it set up for you. You read the date, 6 hours, 22 minutes, or something close to that. Does that sound like what you used before?
I think so.
Okay. I hadn't realized this. I had thought about it. Got it? Now flip this thing over. and it gives a little bit more. And you were, I would say maybe it's this one here. What's the star there? Beetlejuice! There was a movie named that.
That's star name.
No, it's not really. But I can't pronounce it, but BET. EL.
Let me do it so I can do it in the microphone so Bertram and anyone else listening. Okay, it's Beetlejuice, which is BETELGEUSE. Now, there's actually a movie named that. I can't think of the actor. He was a real funny actor that did it. Beetlejuice. They spelled it differently, but that's what it came from. All right. So I think we finished all those. All right. Now let's do our constellations. Who wants to do? Who hasn't done one yet? How are we doing time-wise? Okay. What time do we have to stop?
5:45.
No, 5:15. Okay, we got one.
5:10 stuff here.
Okay, good. Okay, who hasn't done one yet? You got volunteer. You have good friends. All right. Okay, so this is at the bottom. Okay. And where do we begin?
Are we still doing
Right. Yeah, we'll do right ascension first. Where do we begin right ascension? March 21st. So turn to March 21st is right.
Hey, you're next.
Okay.
So March
21st. Okay, you can put it on that thing right there. Okay, and you see the equator and the ecliptic cross right there. Okay, so from there we measure right ascension. How far?
11
hours. Yeah, because don't move anything. Okay, good. Now count your hours. There's 1, 2.
So right
Yeah,
here.
1, 2. Wait. With these little tips there.
So like
1, 2. 11 right there. Move your string up to that, or you can probably read it. What is that? 6 September 6. Okay, move September 6 down to your one down here at the bottom. September 6. Right on. Is that okay? All right. And then you go up 50 degrees. Now here's your equator. There's the North Star. That's 90 degrees. So you're going to jump past 90.
so right here.
Okay. Hold your string.
Straight on.
Yeah, right on the circle. Right. Okay. Go up a little more than halfway. And what are you right in the middle of some constellation?
Leo.
Leo Minor. Leo Minor. Okay, that constellation is Leo Minor. Does anyone know what Leo stands for?
Lion.
Lion. It's the little lion. Little lion. They made a movie about it, but they changed. No, I'm just kidding. Okay.
Galileo.
Huh?
Galileo.
Galileo? What does that have to do with
Instead
it?
of Galileo, he was saying Galileo.
Oh, okay, got it. Oh, boy. Okay, who's next? All right, what a volunteer. We love to see it. Okay, where do we begin?
March 21st.
Okay.
Nice.
You're welcome.
He loves it. Okay. So turn it around till March 21st is right at the bottom there. Okay. 21st, March 21st there.
Oh, now I see it. Okay.
Yeah, that's why everybody gets to try.
They're like in science, isn't it?
March 21st. And then you see that the ecliptic, which is the dotted circle there, crosses the equator right there. That's it. Okay, and then you count from there. How many? 19 hours. And you count this way, and each one of these effects is an hour. 1, 2.
I count which one?
There's little triangles there. 1, 2, 3. Like the face of a clock. Yeah. 19 there, yeah. That'd be 18 right there. And next one is 19, right over there. Pick a time, a date for that. Show it right there. January the 4th. Okay, turn January the 4th till you're down here. Okay. Now it says you're 25 degrees south of the equator. Here's the equator. Now that's 45 here. 25 would be right there. Is there a, I think that may be Scutus. Let's turn over and see what's there. Okay, flip it over this way. Okay. Flip it right under there. Maybe either that or Aquila. I don't know which one.
So it's like maybe 25 degrees right?
Yeah, that's what it said.
Scud or Aquila.
I would say Aquila.
Okay, Aquila.
Okay. Because it was below, wasn't it? Yeah, minus 25. Let's call it Aquila or Aquila.
It's Aquila.
Is it? A-Q-U-I-L-A. A-Q-U-I-L-A.
The Aquila is eagle.
Huh? The
It's
eagle?
an eagle.
Oh, really? I was thinking it was Priscilla's husband, but never mind. Okay, never mind. Okay. Okay. All right, next. Who hasn't done it? Which? Okay, that's the nice to have friends and have places. Okay.
Yeah, that's what I was thinking.
Where do you begin? March 21st, put that at the bottom. Yeah. Yeah, and look, see the equator, which is a solid circle, and they put the cross right there. March 21st. Here. Right there. Okay. Now count. How many? 3 hours from there. Okay, so just like the clock. 1 hour. What's that time? What day? 8, I think it's on those guys. 8:30. 8:30. Turn around to May 3rd, get it at the bottom. Good far, he's lazy. Then go up from there, from the equator, here's the equator, 20 degrees.
I guess in line.
There's halfway, about half of that, about a quarter of the way up. Huh? No, the equator, that's a solid circle. Halfway is 45, and half of that would be about 20 something. Are you in a constellation?
Yes.
I guess
Aries is some close. Let's say Aries. Hey, Aries! This will be, let me read it. I'm trying to read it loud into the computer so people at home can hear it. We said Aries, A-R-I-E-S. Aries. Okay. Yeah, I guess that's closest. This is the thing. It shows Aries as a line between two stars. How do you get a constellation out of a line between two stars?
It's supposed to be a ram, too.
Is it?
So I don't see how they get that.
I don't either. Yeah, okay. All right, next. Where do you begin? Yeah. Yeah.
Is the test we taking today is going to be a take-home test?
No. These are in class. It won't take you more than 30 minutes. But if you haven't had a chance to study these, because you weren't here before.
And then it also may be a conflict in my schedule because I was looking at I was going to run at 5:30.
Okay.
You did me like that too.
Then you might need to get on there, you can come back. We'll do it. Anytime during the office hours. Huh?
So I just go and get a rental for real quick.
Well, how long does it take you to get there? Yeah.
I can get that bad, but then again, I want to
Okay, I don't want to break any laws either, okay?
I'll bring you.
So whenever you feel like you need to go, you can go and then take your test, come in sometime during my office hours. Let me remind y'all when my office hours are. They're not got many of them, but I have office hours on Monday and Wednesday mornings from 8 to 10. I have office hours from Monday afternoon from 3:45 to 6. And I have office hours on Friday from 8 to 12 on the Birmingham West campus. Now, if you're going to make up something on the Birmingham campus, you have to tell me Thursday so I can take it over there, okay? But if you're going to do it Monday and Wednesday, I'll be here. I just don't have many more office hours than that. Okay, you started off at Toronto Economics, right? Did you see that? Yeah. Right there. So 1 hour, right? Right there. What date is that? Yeah, that's right there. Yeah, oh, you could turn, you're so close. You could turn like that. And then you go. Yeah, that's good. And you go plus 60. That's 2/3 of the way up. Whoa, you're right in the middle of.
Yeah,
It's all hard work. Didn't say it. Cassiopeia or Cassiopeia. Okay, I'll spell it for you. C-A-S. Okay, this one is C-A-S-S-I-O-P-E-I-A. Cassiopeia or Cassiopeia. Now what that is, and I finally sort of saw a little bit of how this is, it looks like a W to me.
How do you spell it again?
C-A-S-S-I-O-P-E-I-A. Cassiopeia or Cassiopeia. Okay? Now, what that's supposed to be, that's the name of a beautiful princess, I think she was. And I think it was Neptune fell in love with her. And he was supposed to be the king of the underworld.
He's the king of the
See, well, who was the king of the underworld?
Hades.
Hades, was that his name? Okay, maybe it was him, or the god of the underworld, whatever they call it. Okay? Anyway, one of those dudes that wasn't very attractive, you know, god type things, that he fell in love with her and wanted her, and she didn't want him. So basically he threw her into the sky and tied her in a chair, and that's supposed to look like a chair. It's a W, but if you turn it a certain way, you can kind of guess it might be a chair, okay? And boy, I don't see how they got these things, but they had nothing else to do.
They had to come up with weird reasons for why things happen.
Yeah, exactly. And so they used their mythology to try to explain this.
I guess they were like, that one looks like a W, but let's say it's a chair.
Yeah, well, if you turn it this way, it kind of looks like a chair, a little bit, maybe. I don't know. Okay, who's next? Who hasn't done it? Huh? Ah, okay. Nice volunteering. Thank you. Okay. Where do you begin? Okay. So the whole just block. Okay. March 21st. See March 21st. Oh, you're there. Yeah, that's right. You just showed me. Okay, March 21st. Okay. And you move 13 hours right essentially. Start counting the little hour thing. 1, 2, 3. Yeah, well, it's called right essentially when you go the opposite way. Yeah. Okay, start here. There's 1. 2. Yeah. That right there. And pick the date. It was right there pointing to. Huh? That's right. Yeah. October 4th. Spin that around to the bottom. No, the date. Yeah. Turn that. So October 4th is down there at the bottom. Yeah. Okay. Now, the trouble is you're going 50 degrees south of the equator. Well, here's the equator right there, and 50 degrees is way south. So flip it over, put the whole thing up. The whole thing.
Put it back.
Yeah, that's it. Okay, now read what that is. There. And you still don't get 50 degrees, but it's something south of Virgo. Something south of Virgo. We can't see it because it's even off the scale on the backside. Something south of Virgo. Virgo. Okay? Next. Okay. Right next door. Thanks for volunteers. Okay. All right, where do you begin? Okay. Okay, we'll hold it quiet. Hold it quiet. Yeah. Okay. Put the string down there on the left. Yeah. Okay. Turn this until March 21st. All right, good deal. And you see that's where the equator, which is a solid circle there, crosses the ecliptic. Is that? Yeah, that's it. We're on equals. Okay? Now, you count, which are we on now? 7? 7 hours. So each one of these will be an hour. 1, 2, 7. Okay, move your, okay, you can read that. What date is that? Yeah. July 4th. I'll turn July 4th down here. 4th of July. 4th of July. Fireworks. Okay? And then minus 40 is way off scale because it's 40 degrees south of the equator. So flip it over and see. Still can't see 40, but it looks like it might be the twin.
Gemini.
Gemini. G-E-M-I-M-I. Gemini. G-E-M-I-N-I. Gemini. Okay, good
6
deal.
minutes until it's 5 o'clock.
What's that?
6 minutes until it's 5 o'clock.
Until 5. Okay, we got a little bit of time. Let's see how far we can go. Okay, that was the sort of fun part. Everybody got, pretty much everybody, ah, in the corner, you snuck out. Oh, yes, you did too, Reggie. Okay. All right. Let's go to part D. Relative amounts of daylight and darkness. We talked about this already in class. Question, okay? Now, we don't have a globe, so when it says rotate the globe, we have to use this. So I think I'll show you what to do. On the ecliptic, locate the position of the sun on June the 21st. Okay? Now, the sun is always on the ecliptic. That's what the ecliptic is. It's the path that the sun makes. So let's turn over here and set up for June 21st. Whoa, I just missed it. Right there. Okay? And the sun is on the ecliptic. And the ecliptic is the dotted circle right there. Everybody see it? That dotted circle, that's the ecliptic. That's where the sun is. Okay? Now, what I have to do is pick something that represents the sun. There it is. It's a part of that tick mark. There's a tiny little star right there. So what I'm going to do is turn this until the sun is coming up just over the horizon. Okay? Here's the horizon here. So I turn. Oh, almost there. Right there. And then put the string right there where the sun's coming up. And what time is that? It looks right around 4, you want to say 4:30, 4:20, what would you say? There's 4, there's 5. Let's see if I can get it on that again. Right about there. Let's say 4:20. Okay, you can write that down. That's not your answer yet. Okay? But that's what we're doing. Note the sun's declination for this day and record it in the table. Now, what is the sun's declination on June 21st? What do we know about June 21st?
It's a
Say again?
It's called right answer.
It's the summer solstice.
Summer solstice. So what was the okay, here's a correction. Make it in all three places. On page 366, those tables there, they say the SEC of the sun. The sun has nothing to do with the Southeastern Conference. No, I mean, that's DEC. I don't know why they did it wrong. It's declination of the sun. DEC of the sun in table 47.1, 47.2, and 47.3. DEC of the sun. Okay? And what is the declination of the sun on June 21st? Say again? Okay, it is summer solstice. What's the declination of the sun then? Declination of the sun is how far it is above or below the celestial equator. What do we know about summer solstice?
It's way up high.
Way up high. How high does it go?
Plus 90.
90? No, I don't think so. Okay, no, not that high. 23.5. You're absolutely right. 23.5 degrees. The declination of the sun on June 21st is 23.5 degrees. Okay? Now, you can put that, you can do it plus 23.5, 23.30, whatever you want to do. Make sure I can understand it. Okay. Now.
Mr. Fowler.
Yes.
Oh, I was just saying, is it heating here? It's cool.
I know, I have no control. You see, they put a box over there. We used to have a thermostat, and we used to adjust it. They don't let me do it anymore. Yeah. They just do a new system in here, so it should be better than this. Here's the other question they had. Remember, I got the sun here. I've lost it now. Where is it? There it is. Right there it is. The question is, does the sun rise due east? Is that what it asked? In the east on that day. Here's the east right here. It's actually rising north of east. So the answer is no, it rises north of east on that day. Okay? Now, and did y'all write down 4:20 a.m. was when the sun came up, right? Did you write it down? That's what I read off here. I asked, did y'all think it was 4:20, 4:30? Y'all said 4:20 with a little prompting from me. Okay? Now we need to see when the sun sets. So that same little speck there that I was using as the sun, we're going to turn it around here. It's this little speck right here. Okay? Turn it around here until the sun goes right down below the horizon. Okay, I'm getting lost here. Okay, there. Where's my speck? There's my speck. Right there. Okay? Let's see what time it sets. It sets about 7:40 in the evening. 7:40 p.m. And by the way, it sets north of west. Okay? It rises north of east and sets north of west. It makes a big old arc across the sky. That's why it takes so long to do it. Okay?
Are we supposed to be filling that in?
Okay, no, you just write it down on page 365 somewhere.
Okay.
Okay. Now, I'm going to clear this screen and okay. So what time was it rising?
4:20.
4:20. That was a.m. Okay. And what time was it setting?
7:40.
7:40 p.m. Now, I was in the Navy, and I'm used to military time. Are any of you?
Yeah. I mean, a little bit.
Okay. How would you write 7:40 in military time? Second? 1940. You add 12 to 7, and you get 19. 1940. You don't have to have the quote. Yeah. Let's subtract that and see what we get. The question is, Okay, I can't find the question. Okay, right there, bring the sun back, counting how many right ascension hours. Okay, estimate nearest 15 minutes, the amount of time the sun is above the horizon. In other words, the amount of daylight. And what would that be? 15 hours and 20 minutes. Okay, 15 hours, 20 minutes. That's what you put on the thing. Now, let me say this. You might notice, say, I don't think it's that late or whatever, that long a daylight. It may not be. And the reason this is set up for 40 to 50 degrees north latitude, guess what? We're at 33 degrees. So it's not going to be that big for us, but this is all we got, so we're using this. Okay? So that would be number of daylight hours. What did we say? 15 hours and 20 minutes. Okay? Number of hours of darkness. How could we do
I
that?
would assume that we could figure that out by subtracting the amount of daylight hours from 24.
Exactly. So let's do 24. Only I'm not going to do 24 because I'm lazy. I'm going to do 23 hours and 60 minutes. Isn't that 24 hours? Yes. Okay. And subtract from that 15 hours and 20 minutes. And what do we get there? Second? 8 hours and 40 minutes. Is that what you said? Okay. And I'll admit that's a little bit shorter than our nighttime hours in summer solstice, but it's not too far off. I imagine we get closer to 9.5. Okay. Now, we were one summer, right around December 21st, my wife's family took a vacation up to Canada. What was the region there? Goodness gracious, Banff and Lake Louise, Jasper. Oh, it starts with A, I think. I can't think of it. But anyway, beautiful country up there. But man, it seemed like it took forever for the sun to get dark. It was after 9 o'clock when it got dark at night. And then it was light very early in the morning. Of course, I was still asleep then. I mean, because you get closer to there, you're getting closer to 24 hours, okay, of daylight. All right, so we've answered that. Now let's go down to December 21st. Someone want to try that? Reggie? Oh, yes, thanks for volunteering. Okay.
Was that for June 21st?
What's that?
That was for June 21st.
That was June 21st across the board. Okay? The declination of the sun was?
50.
Second?
23.
23 degrees, 30 minutes, or 23 and a half degrees, however you want to say that. Number of daylight hours was?
15 hours.
15 hours, 20 minutes. The number of darkness hours was?
18 hours.
So we are not doing 11 and 12.
What's that?
We are not doing 11 and 12.
Okay, we haven't gotten there yet. We're still doing, it says repeat this for December 21st and March 21st.
It's 506.
See, we're still doing this. Yeah, we haven't gotten that.
It's
Okay.
506 now, just like.
What's that?
It's 506 now, just like.
5 till 6?
506.
5:06. Okay.
I was just going to let you know.
Can we do December 21st, you think? Yeah, you're fast, aren't you? Okay.
You got it.
All right. Now, okay, flip it around.
0.5 degrees.
Okay, what we're going to do is December 21st, and move to December 21st. Right on that yellow. December 21st. What is December 21st?
The start of winter solstice.
Okay, right around it. I'm trying to line it up. Yeah. And that's winter solstice. Tell me something true about winter solstice.
It's cold.
Yes. Go ahead. You know, I was looking the wrong way before. No wonder. Okay, never mind. Okay, December 21st. Okay, there's the ecliptic. Okay, and pick. That's where the sun is. Okay. Now, yeah. Hold that right over there. Oh, no, not.
rise there.
Why? Are you saying that?
Okay, let's just pick that. See that right angle there? We'll just pick that place in. Scoot this around until, scoot it to the east. Little tip there, keep on going. So that was just about the rise over the horizon. Okay. That little square, keep going. Keep going. Oh! Oh, right there. Okay, move your string over there so it's right on top of that. Right there. Okay, that's when the sun rises. What time is that? Okay. It was 4, 5, 6, 7. Okay, what was it? December 21st. Okay. It was 5, 6, 7. About 7:40 a.m. Would you say that? Okay. 7:40 a.m. is when the sun rises. Okay. Then, yeah, that's where you're going to do the stretch work. All right. Now, I forgot to say this earlier while we're doing this. Didn't I tell y'all early on that you can always bring the formula equation sheet to every test? Okay, good. I want to make sure y'all do that. Yeah, you can bring a formula and equation, anything you want to write down on a piece of paper to every test. Okay.
Except for this one.
No, this one you could have if you had done it. Okay. So if you want to be writing furiously, you can. Okay. Okay. All right. Now that same spot. Turn a little bit so we can see it again. Yeah, there it is. Move that little square around so it's just getting ready to set.
It's 5:10.
Okay, we need to stop all this. All right. Oh, we did do it. Little more. Right, like that, right there. Okay. Oh. Oh, right there. Right on December 21st. 7, 6, 5. What was that? 4:20. 4:20 p.m. 4:20 p.m.
Is that?
Okay. So what time was it? Did it rise?
7:40.
7:40 a.m. and it's set at 4:20 p.m. Okay.
So I would assume that since it's basically the reverse of the one that we just did,
Yeah.
for the number of daylight hours.
Very, very good observation. This would be 1620, right? Okay, but let's make it 1580, right? Borrow 1 hour and that's 60 minutes. Subtract, and what do you get? 8 hours and 40 minutes of daylight, which is just, yeah, exactly like Thomas Earl was saying, exactly the opposite. And how many hours of darkness would that be?
15 hours.
1520. Now, we're not that far north, so it wouldn't be quite that far for us. Okay? We'll have to do March 21st next time. That's where we'll pick up. So what we'll do next time is we'll start 2 hours on chapter 15 where we left off before. I think in those 2 hours we will finish the chapter. I think we will. Okay? Now, yes.
What's the declination for December 21st?
Oh, good question. What's the declination for December 21st?
Is it the same?
Yeah, 23.5.
You think so?
Is it 23.5 degrees?
Possibly, but is it the same as January? I mean June?
No. So is it Negative.
Negative. You're south of the equator. So that would be either minus 23.5 degrees or 23.5 degrees south. You could say it either way. For June 21st is north and December 21st is south. Or plus or minus, however you want to say it. Good deal. And you got the hours of daylight and darkness. Okay, then if you are red-eyed and you want to take the test, now some of you were not here. Well, I think all of you, all that we have left, were here. If you feel like you are prepared for the test, you can do it. If you want to wait till later, you can. But don't wait more than a week. Try to get it done within a week. Because we're going to have another test very close to a week. Okay? Anyone who's ready for it? Get your formula and equation sheet out if you've got it. And if you don't have it and you want to write down some stuff real quickly, you can. Or if you want to write it down and come back and take it later, you can do that as well. So, anyone want to get it started, okay? All right. Now what we'll do next time, 2 hours of class. Well, if we finish the class within 2 hours, well, okay. If we finish the chapter within 2 hours, let's do it this way. Let's go on and start the class next time with the lab. Finish this lab first. Once we get the lab finished, then we'll go back to chapter 15. If we finish them before 3:45, we will have the lab on chapter 15 starting at 3:45. And we'll have a full 2 hours. No, yeah, full 2 hours to do it. Sound okay? Right. I think we'll have time to finish the lab then. Finish the class. Okay. You can have formula and equation sheet. I don't think you'll need scratch paper. If you feel more confident with it, you can have it. Okay? And you'll read the test. Okay? That's one call. Are you going to wait? Oh, you're going to wait? You're going to wait? Okay. You got this next one. Okay. Wait. Give me my thing back. Okay. But you're going to take it? Not going to commit, huh? Just wait. Okay. Decide whether you're going to take it or not. You will. Okay. That's your, yeah, you'll turn that in next week when we finish it. And I've lost my thing again. Yeah, you write on that. Write the answers on the paper. Good deal. Have a good weekend. Oh, by the way, y'all know about the good news, bad news situation, right? Yes. Okay, the bad news is there's no school on Monday. It's a holiday. It's Martin Luther King Day. But the good news is it doesn't affect us any. We meet on Tuesday and Thursday, so good deal. All right. I'm going to turn off the projector. Well,